还没开始呢，你是volunteer是吧？这display 怎么弄啊？
我也不知道。
你不是这学生吗？
我没来这儿讲过呀。
刚才按了一点效果也没有。
没有其他的光听吗？
我
给你找一个。
Does anybody know how to turn on the display? Okay. Oh, I can't. 还是视网没问题。好像是25分钟，怎么知道
25对。
我是
你什么呢？不知道。
Hey, do you know how? This one. I press. Yeah. Hey.
Is it not showing?
Yes. This one.
Let's make sure that one's there.
Oh, looks like it's.
No, it's a different one.
A different.
Yeah.
Hello.
I think it's off.
Oh, while I'm speaking, can I remove the masks? Yes.
Yeah.
Hello. Oh, cool. And I have one demo, so turn it off.
You didn't happen to have an adapter, did you? Like a USB-C adapter?
No, I didn't bring that.
Yeah, 'cause this is, it was working
But
fine.
you know what?
Mhm.
I have the slides on my USB drive, but if you can provide a computer that can.
No, we don't have any other computers. So let me. No, let's see.
You just
Not sure because it's not.
suspected that.
Might be the computer.
Now,
So I'm gonna call and see if I could get. I'll try. Oh yeah, that would be awesome if we could try.
thank you so much. Oh, that's yes.
Yep.
To HDMI.
We really, really had any issues so far.
Before?
Yeah, no. Okay.
This is good.
So let me see if it shows up.
check my slides. Make sure.
Losing that's today. Mm. Is Mackenzie there? I need a few dumbos. Okay. No, I haven't, but I never know if he's in. Okay. Yeah, yeah, they're good. We just need to put on those here. So, maybe had some issues usually like I'm not able to display on this computer.
Okay.
Yeah, so I have to call Mackenzie real quick so we can get some numbers in there.
Yeah. Like a permission state computer? Or?
No, I honestly don't know. Because when the time when I was using Overwatch Nokia, it actually was working. No, nothing. Even with that adapter, it didn't work. So she's trying to find a function station.
Did you set it to go to the other display?
Yep, I just said. I said it before, but the
Yeah.
second time when she had the.
Let me see if I'm at least getting it at our screen. Yeah, you can use mine if you need to. Like, it's fine.
Yeah.
But I doubt. You're on Wayland, right? What OS are you using?
A Fedora.
Fedora?
Mhm.
I think it starts with Wayland by default. I don't know.
Oh, you're assuming that we need to change the mode.
I'm not sure, but
Yeah, I have the slides on the ESP side.
yeah, we can try.
Yeah, we can try. Thank you so much.
So it didn't work on a straight out HDMI either.
Now, yeah, well. My teammate gonna try on his computer to see if the screens work. If the screens display, then I will put the slides on this computer and display on it.
Right, the top copy I was going back.
Oh yeah. Do something. What's your system real?
Is this Telematico? No, it's just.
He's different computer.
Yeah, it's a different one drop down.
Thank you anyway for the help. I just wondered, would that be possible? Because currently the light was all on. Would that be possible without connecting the Quarkus to see if the machine actually works, the projector actually works?
The project, yeah, we've had other sessions in here today.
Today?
already, yeah.
Yeah, we had it seemed to be fine, but can I try and have it?
Yeah, sure. Yeah.
I wonder if the display like resolution on this is too high. Do you know
Can you
if they're
see it in the representer? No.
I'm gonna try lower display to like
Usually, yeah, it shouldn't be.
Can we somehow do it in the other way?
Let me see.
yeah, I just changed the display. I'm gonna try to plug in and
Sure.
see because it detected it last time.
Yeah.
But it didn't
I'm gonna do a power cycle.
You need help? I can do that.
Yeah, we just did a power cycle because it's not projecting. Let's see. Yeah.
Oh,
No. It's just this one, I think. Because it's like so. Okay. Oh yeah, like if we can do it on the big phone. Oh yeah, yeah, the phone. She got it. Yeah, great. Yeah, yeah.
I'm gonna run one of these through small.
Yeah.
You need it.
I still want to just in case. You never know.
and because I have a demo, I mean, record the video on the slides. Follow the times. And the, if I only connect to video gas with the sufficer to stream the video.
So yeah, somebody like a volunteer will be back there streaming the video for you. So
I have it on the slides. But, let me try. see the
Let's try
bandwidth
now.
allow me to do that.
See the mouse should
Nothing
I'm
here.
gonna give that one again.
Display crash, but that's okay.
Yeah, it's working. See?
This?
At least the
Possible boxing to power cycle?
Yeah, I don't think it's that. I don't think it's that big issue. It's probably wrong. I'm gonna call somebody. Alright. So we're having some issues in Terrace Lounge because the projector is just not really working. We did a power cycle and it's still not displaying anything. I don't know if there was anybody that could take a look from there.
is this caused by the input off?
Okay, do you have his number? Yeah. Yeah, if you can do that. Yeah. Okay, yeah. I'll keep going with that thing. Yeah, 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 yeah. Do you mind looking for an extra HDMI and two actually? So we can just replace, yeah. Oh, no. We're gonna try cables, and if anything, we'll just have somebody bring in another projector.
Okay.
So, yeah. So I'll just keep trying.
这样我一点都不紧张。YouTube 吗？哦。
Here, I got another one.
Oh, the video stream, the recorded demo just cut up from time to time. I mean, for some reason. No, I mean, anyway, but.
So, well, I guess we'll call him.
Oh, anyway, I have the local video. Let me check. Yeah, I should have the local. I know. Oh yeah, I have the video local in case I probably output the local video.
Oh, what do you mean?
I have the video not on the YouTube. I put in the local directory.
Oh, okay.
Okay, so in the demo time, I will exit from the slideshow and play the local video just in case
okay.
the streaming didn't work.
Yeah. There we go. 6.1.
Yeah, I think probably that's the best option to avoid any interruption in between.
Yeah. So we have somebody trying to cut out the projector right now. I'm gonna do another phone cycle. Just um, screen outside here.
Oh, the monitor? I don't think so.
That would be another option we could do
True.
for now.
Isn't it bringing them up?
Yeah. He is. Yeah.
Or are we going to tap that up?
Seriously? Maybe to smell the balloon.
Me?
Yeah.
How long ago was that message?
Just
This up?
now. Just now. He's on his way. Projector. And
I think there might be a longer CNI involved, so I'm gonna double back on that.
HDMI to VGI. Yeah, I have a card table. So yeah, just one thing VGI to VGI to HDMI.
So I'll pick up the output for here from the podium
Or
actually.
is one here in the wall?
There's also one over there on the wall.
Go around. There's one right here.
Take one. You're just going directly. Right.
Yeah, it's still going.
Oh, yours.
Yeah, I mean, we need to do that stream, right?
Wow. Yeah, they use another projector. It works now.
Also got a 7-8-inch TV at home.
We could do that as much.
I don't even know what the Can I go look for another projector if you want?
It's for normal screen, right?
Yeah.
Yeah.
The stream is fine. You're looking fine on the stream. It's just unfortunate.
Okay, so on the screen, it's fine.
The stream is fine. Yeah, sorry.
No, it's fine. It's fine. Because
It's one of those.
I know it's
But, yeah, I'm gonna have to ask them to just keep my computer here. So you ready to bring your laptop here? Alrighty.
你那边有 timer 吧？回头计时就到10分。OK。Do you shred this one? So that needs to be mirror. Adapter? Yeah. Come on. Oh, I can put slides in that computer if you. That would be better.
Yeah.
Okay. Let me kind of get slide.
You're not even getting anything right now.
Let's use that computer.
Oh, yeah.
This one didn't work either.
Okay, I think it's the swapping of the computers all the time. It's making it signal. Do we have another deck setting?
Man.哦，等一下，这是不是，都是 web swap。So,
Hey man, go ahead and grab me some lunch.
yeah, but it's all wrong. So, it's got delayed after lunch.
Yeah, unfortunately, we just have to look into this.
We have to continue.
Right.
Oh, yeah, okay.
Yeah.
Yeah, do you want me to grab you something? Like,
Just grab, put it aside.
yeah.
Yeah.
Do you have a preference on things?
No, nothing.
Any-
Not pick it.
anything?
Yeah, anything. 对，但是一样的，如果我放着。
Try straight in.
See, it was working, and now it's not
Have
working.
you tried this game straight on the computer? It's just for you.
Yeah, so I guess just try this video. And then
Let's skip now. Yeah, I have a.
we just have to get
Just roll with it.
we have the
Oh, get
camera.
it otherwise shot on the camera.
Yeah, yeah. So right now we're just going directly to the projector, so the content will not be there, so we'll have to shoot the camera so that people can see on the slides, can see the slides. Or
Sorry, I didn't get it.
so right now, so we're not able to bring in just the content.
Mhm.
It's gonna be the camera, so people will see you and the slides
Mhm.
through the camera.
Uh-huh.
But because before we just had like just the content, but
Oh.
for now we just
Both.
have you both you
No,
and the
it's fine.
slides. Is that okay? for
Yeah,
now?
as long as.
Because
Yeah.
we just have to, you
I
know.
thought we cannot wait anymore.
Yeah, right. Yeah. So yeah.
Yeah.
We just have to come back to this room after you're done and just see.
I assume if I have the problem, other people will also have the problem.
Right. Yeah, to the audio. We should be good.
Should we good?
Yeah.
So I
Yep.
can start the talk?
Yep. You can start at the top.
Let me see if I can display.
I connected the DI, so yeah.
Okay, finally, we fixed it. Yeah, and thank you so much for the patience. And let's get started. And my top. Let's first introduce myself. I'm Owen. I've been working in Red Hat for about 2 years, and primarily I'm working on the network role, and it's Ansible module, and I also working on some network managed stuff. And the topic for today is modern network config via Ansible network role. And just wonder how many people use Ansible before? Can you show me hands? And how many people use network role before? Oh, you do use? Okay, because network is so powerful, but it's underutilized. I'm glad that someone here today actually use it. And Ansible is a tool that can make the IT automation that so easier. Because imagine you have a huge fleet of machine. If you want to configure on those machine, maybe different settings, or those machine might be varying OS and other system components. So with the Ansible, it can configure them all at once.
and with the zero downtime, and rolling the updates with the load balancer easier. And while the network role is an Ansible role, can be used to manage and configure the networking setting to the managed host. And the machine, of course, might be varying OSM versions. And providing such a tool to automate the configuration process. And because conceivably the requirements and standards might be changed, but with the tools, it can just everything happen automatically. Because user only, it's a declarative API, so user just need to provide the settings. So the module abstract like a black box and configure setting for the user. And before the invention of the network role, and there are already some other modules like other networking tools like Network Manager or Network MCLI. And the power of Ansible is because using the Ansible facts, because gather status info from various machines, right? And in the inventory, you can custom some settings. In the playbooks, you can retrieve the setting and pass as a parameters to the module. So it's very convenient, and it's automation so that you can do some parallel configuring, and which may make the configuration process just be simplified. And the network will also provide very good error handling and or error reporting, and also can do the checkpoint and rollback when error happens. And because I know some user might still stick to the old legacy way for configuring the networking. Now network role still have two providers, both Network Manager and InitScripts. And currently, there are two primary modules in the network role. The one is network connections. The other one is network state. For the network connections, they have two providers, InitScripts and Network Manager. And it basically creates the connection profiles for the device and activating the connection profiles. And for the network state, instead, it just configures the device directly. And it's accept all the M-state state examples. Okay, here I draw a very vivid comparison between these two modules. Because network state just implemented, I think, a couple of months before. It's just brand new. For network connections, cannot do partial configuration. You have to track all the configurations. But for network state, it can. And the providers, network state, I mean, the thing behind it, it's just still using the network manager, but the network connection can use both InitScripts and Network Manager providers. And network connection can configure the device, or cannot configure the device clearly. It always creating the connection profile at the first stage. And the supported feature, I think various interface types are supported for the network connections. And recently, we just implemented various new features like policy routing, various bounding modes and options, and the ETH2 setting, DNS setting. But for the network state, since its backend is libm state, and all the features in the libm state that are also supported on the network state. But I know that for the network state, it's full-fledged. So I assume that almost all the features are supported. And here is an example for configuring the IP address for the Ethernet via the network connections. Since it's Ansible, we have to specify the hosts. We need to include the role, and we declare the variable to be network connections. And what the name is the profile name, and the type to be Ethernet, and it's on boot. And we configure for IP. I configure IP for them. And there's other way that configuring networking, which is network state. Similarly, we need to import the role. We declare network state, and we specify the IP configuration. Originally, the network connection was invented. It's very good for whoever or for the user stick to the init scripts provider, because network state cannot use init scripts provider. You can only use the network managed provider. Well, with the both provider for configuring the with both module, you can configure the IP address for the Ethernet though. And for configuring the routes and DNS and network state have some global config, but actually it matches the interfaces in the system and config on the device. I mean, per device will have the route and the DNS setting. And similar, you can do this about the same. I mean, achieve the same effect via the network connections, but I didn't list it here. Here is another example for configuring the wireless connections. And since for some system, they might not install the network managed Wi-Fi, because currently the wireless connection can only be supported for the network managed provider. We cannot support it. We didn't support it in the init scripts provider. And we just specify IP, choose the, here I was choosing the SAE, WPS personal for authentication. Here's a complex example for configuring the policy routing. It's just implemented recently. Here's we're using the network connection module. We define the route, and we add different routes to the routing tables. We define the routing rules from like source routing and the source port range, so that it can forwarding or filter port packet correspondingly. And this is configuring the bonding options. Also use network connection module. So utilize the bound, so we can have a feature like link aggregation, and if any failure happen, can fail over to another link, right? And we can create the controller device and add the ports to them, and choosing different bonding modes and define different bonding options. I make a demo for the policy routing. So let's take a look at it. Hi, everyone. Today I will give you a demo on how to configure the policy routing through the network. Let's first take a look at the testing profiles. In the testing profile, we specify host since it's sensible, and we initialize the test interfaces. It's created by the IP command.
Sorry about that.
And we import the role. And we specify the networking config under the network connection variables.
On my side, so but
and we specify the profile name, interface name, state to be on, and the type to be Ethernet. It's auto-connected. We configure both IPv4 and IPv6 addresses. We create the route, and everyone add the route to we add the static route to the routing table. We also configure the policy routing through the network. Let's first take a look at it. Hi, everyone. Today I will give you a demo on how to configure the policy routing through the network. Let's first take a look at the testing profiles. In the testing profile, we specify host since it's sensible, and
we initialize the test interfaces. It's created by the IP command. And we import the role. And we specify the networking config under the network connection variables.
I'll try to explain. Oh,
And we specify the profile name,
don't know why this
interface
slideshow-
name,
you can
state to
see
be
it
up,
now.
and the type to be Ethernet. It's auto-connected. We configure both IPv4 and IPv6 addresses. We create the route, and we add the route to we add the static route to the routing table. We also configure the policy routing rules.
So I cannot control
In another
the,
terminal, let's actually run
pointer,
it to see
the
the
mouse.
effect. Here, I was using the QCOL2 image for test.
everything.
It's QEMU copy on right. It's very convenient and suitable for testing. We can see the in another terminal. Let's actually run it to see the effect.
Assume we have to use it all the way.
Hi, everyone. Today I will give you a demo on how to configure the policy.
Is it better?
in the network. Let's first take a look.
Okay, I can explain another way.
in the
Wow,
test
the resolution on my computer is better than this one. But anyway,
and
so
initialize the test interfaces.
I'll mute.
It's created by the
So we initially we just initialized the test interface, which created the VAS by the IKIMP command. Then we import the role, and we define the profile name, interface name, state to be up, and configure the IP, the route, and the routing role. The routing rule, and yeah, this is basically for the policy routines. And in another terminal, actually using QCOL2 image QEMU copy on write. It's very convenient for testing purposes. And we run the role. Yeah, currently, I was using the network connection modules. We're running the role, and okay, it starts running because the role have some default tasks. It's running, maybe install several packages, depends on the module I'm using. So it should take but it's gonna be very quick. And here are some assertion steps. Just like I said before, just install several packages. Basically, what I did is just after configuring our SS edge into the machine, use different IQ command to verify what I did is correct. So I get the credentials. Now the Ansible playbook, the playbooks actually passed. See no errors. So I get inside the machine. I use IPS show ETH test 0, and it displayed. I didn't block it. It displayed the IP address exactly the same as I just configured. And it's very convenient as a user because you just do not need to memorize all the commands, just provide the settings. And let's take a look at the route that we added to the table 30200, and another route add to the table 30400. It's also matched with the route I specify here. And finally, I need to verify the routing rules. The policy routing rules. Still using IQ command. I mean IP route list show table to find all the policy routine rules. You can clearly see it's a source routing, and from all source ports 128 to 256. So it's correct. And Also, the traditional routing for the packet going to the address 198.51.100.5a was also added into the routing rules. Yeah, I think primarily that's it. I have not made you, but given the fact that it's not complaining, but given the fact that limited time and it's kind of poor resolution, I will stop for now. And thank you so much for the patience. I will answer some questions if you have any. Mhm. 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 Uh-huh. S- So let's try to repeat your question. You said that you try to use an open base switch to make all the nodes, managed hosts at least can talk to each other. What's the module? Uh-huh. Uh-huh. Okay, okay, I see the point. So that the machines kind of isolated, cannot talk to each other. Uh-huh. 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 Mhm. Uh, for now, I do not, because you're talking about the tune and tap interfaces. Currently, um, that's not supported for now. Yeah. Did you try Network Manager? Did you try Network Manager? Oh. Yes, yes. But for your problem, currently, the role cannot configure the tune and tap interface. Uh, but I haven't tried it out in the network state. I don't know, but at least for network connection module, it cannot. Yeah, it's just released. I think probably a couple weeks ago, 1 month, and I will keep that in mind to see if network state can configure the tune and tap interface and make the and create the VMs so that the VMs can talk to each other. So your question is when we reboot, if the configuration is that's well here this thing I want to mention is that for the network state module, we do not do any validation error handling. Basically, we're just passing whatever the parameters user providing and feed into the libm state. So I would assume that libm state will do the either restore, like you said, or save the configuration somewhere. Yeah, but the role didn't do that. Yeah. Mhm. Any other questions? Okay. If now, then probably that's all for today. Yeah. Thank you all for the patience and participation. Yeah. Thank you so much.我都习惯了这种场合了。以前对以前弹钢琴，以前弹钢琴也是，在家练了200%的实力，上去能发挥20%就不错了。看不出来你还这么内秀，还练过钢琴。也练过琴，学古典挺好。没有，我觉得反应挺好，就是有点可惜，就是那个 demo。它这个设备确实。Are you outside? Yeah, I'm outside. I just finished it. It's recording, right?
I believe so. That's what. Yeah.
I wish so that. Yeah.
Yeah, that would be Legman question.
Layman, because it's kind of parsing the regular time window.
Right. So it should still be your stream because they're not stopping your stream anyways. Was this the one this was the one I had, yeah. Okay. You know what?
But still, in the demo time, you have a couple problems. Yeah. So, I mean, yeah, I didn't have time to play all the demos. But...
Well, yeah, that's what we're gonna do right now. I'm just gonna come through and.
Did you have lunch?
Hmm?
Did you already have lunch?
Yeah, we'll be fine, but it's fine. Just gonna get this working.
You had lunch, right?
Oh yeah, don't worry.
Okay. Hard work figures. Just make sure I didn't left anything, otherwise you can be in trouble.
It's definitely about 70 because the projector works
Straight in.
yeah. Right now it's just I'm trying to switch the video off. And it's not.
It's full band. Here, I don't know. He sees us up here.
Hey, both. So it's definitely the top 70 because we were able to get projection directly. Yep. And once we have this set up, went to blue now. Before it was black. I did what Nate suggested to switch the video output to 1080.
Yeah.
Did that?
What was it on 1080i 59.4?
Yeah, it was. And then switched it. I switched it to 1080 1080p 59.4.
Yeah.
I waited for like a month. Right now I'm at 16.
That's the source, right? That's the source. That button's green.
Right.
Is it on your mind?
Oh, so I had a teacher and one of This is a good one.
That's putting out the mirror.
So if you it's loud.
Yeah, it says it's duplicating. Let me try extending it.
It's getting here. So that's good.
It's not passing it out.
Let's see, since he's green, let's see, 7.
weird is like when I change the output, the source button changes from. Right?
back on, everybody.
Oh, it's that kind of presentation. Huh? No, I'm used to working remote. Fully embrace the newscaster thing. Okay.
Remember not to stand up during meetings.
I mean, they should be here. We can put it over there. Hopefully they'll show up. Yep. Everything's getting live. Yeah, so the recording will be there, but they're not like, they won't be covered. I think no problem. Oh, that was yours? Okay. Yeah, so the live stream was on the whole time. So, you know, the video is here. You know, if you want to go look at it yourself, if you want to do some editing, you know, you can post it and not have it. Right. But they can policies do that work. There's no, it's not for free, right? So, we will hopefully get people to go to those to do all that. Many hours of work. So, okay. But the like the raw version is public now. Okay. So, yeah. Thank you. Yep. Well, top here. Do what? You know what the top here is? We're supposed to be on testing, but I'm just here, so.
Tester's guide to quality, but yeah, so it's about 7 minutes ago. But only a few minutes.
I'll give somebody a call 1 second.
We are conducting this research, so thank you for waiting.
One second.
Whose laptop is this?
I'm not quite sure.
That doesn't sound.
Hello, my name is Mesut Turkal, and
The first talk is a virtual talk, and thank you for waiting.
Yeah, very sorry about that.
I'm very happy to meet with people passionate about software
It sounds really
development
soft, right?
and the best development.
How do I ask questions? Do you have like the channel?
Yeah, so we'll have him hop on call at the end. Is there any sound setting we could change here? I really hope that. Let's see if that's better.
Practices, and of course discuss about ways to
It's still
improve the
really soft,
efficiency
right?
and minimize the cost in our workflows. I'm a
Users not available to come.
Yeah, is this?
Yeah, that might be me, I open SUSE agent.
Oh,
With different timing.
yeah, this is. Sound is coming out great in the other ones.
I try my best to work with the
Let's see this.
outside the world.
Quality assurance engineer, and today we will talk about different
perfect.
quality assurance practices, and of course ways to improve not the
Yeah,
quality,
can you
not
make this
only in
any
our
louder?
product.
So
Oh yeah, we.
I think it's at max volume.
Oh, hold on, because I have it turned down there. So
Okay.
I'll just. Let me just.
This is the virtual ones, yeah.
Okay, so we're not getting content on the screen, so I'm just going to do a test camera shot.
Okay.
to meet with people passionate about software development and the best development practices, and of course discuss about ways to improve the efficiency and minimize the cost.
Yeah. It's on max volume. Both of these.
Maybe the video is probably a little low.
In our workflows.
Can't make it any higher.
I'm a quality assurance engineer, and today we will talk about different quality assurance practices, and of course ways to improve the quality not only in our product but also in our processes and the life cycles, the workflows that we follow as well. So I'll share a journey and a story, including lots of different initiatives that we have performed in our teams. And as we will see, these initiatives are performed by a strong communication and a collaboration with the other teams or the other team members, because quality assurance is not only testing, but including lots of different stages, starting from the analysis of the system, analysis of the requirements and the specifications, the customer expectations, or the end user's expectations, until the maintenance stage, which is raising the issues or the improvement points or the vulnerabilities that we find to be fixed or to be improved. So we will try to cover all the stages one by one, and we will cover all the rings of the whole chain, because quality assurance is not achieved by individual efforts, but it should be a holistic approach. So we will see lots of communication channels performed and maintained by the other teams or the team members, and we will see how closely the quality assurance members should work with the other teams, with the product managers, with the product owners, with the development leads of the development or the development team colleagues, development team members. So as a result of all these initiatives, we will see how the outcomes will improve and how we will increase the visibility of the quality assurance activities and the practices. So starting from the system under test, clarifying the system that we test and we develop mainly is very important as a starting point. Because if we don't know all the aspects of the product, all the specifications, all the features, all the use cases, or if we don't know what the customers or end users are expecting from this product, then we will not be able to check if the actual behaviors are meeting with the expected behaviors. So making all the requirements and the features visible and understandable is very important from the first place, because assuming that most of us are working with agile practices nowadays, and as agile suggests, the working product is more important than the comprehensive documentation. But it doesn't mean that we don't need any documentation at all. We will still have to put some effort on making some documentation to clarify the features and at least making them understandable and visible to everyone, because otherwise we may have some misunderstandings. To make everyone on the same page and to have the same understanding, we have to make a basic documentation. It doesn't necessarily have to be a comprehensive documentation, but at least some documents explaining the usages and the features, the aspects of the product will make everyone be clear about the product and the expectations. And in this way, we can even improve the testability. We can figure out what kind of testability issues we have, and we can figure out what kind of coverage rates we have. So these were the very first initiatives that we have done. And one more thing we have agreed with all teams, including the development teams or the product teams, was to encourage the early QA involvement. Because if quality assurance members are not aware of what is being implemented at the moment, then they cannot start their preparations in the meantime, right? Because in agile workflows, the efficiency is very important. We have a very limited testing window, so we have to already start our testing preparations when the design is already started to be set. And if we are aware what is being implemented, then we can already discuss about the testabilities and all the aspects of the requirement as well. So what we have agreed with the other team members was to building a strong communication channel. And whenever they start a new development activity, the quality assurance members were invited to the discussions of the requirements and the other aspects of the product. So after this stage, all the system level clarifications and the analysis of the requirements, the next thing that we do in the software testing lifecycle is designing the test cases. Designing the test cases is again very important to cover all the use cases, because otherwise if we have some coverage issues, if we don't properly cover all the use cases, then we may have some production errors or some bugs. If we test some features with only a specific data sets or a specific data type, then it may not be sufficient to figure out all the possible problems or all the possible issues which may raise in production. Because if the feature is supporting lots of different data type in various data ranges, then we should prepare a comprehensive data input, test input, and cover lots of different regions. Let's say if we are developing a user interface which is supposed to execute on lots of different browsers, then we have to do the cross-browser testing as well. So we have to figure out if there is any compatibility issue, then we have to fix in advance, not to have any surprises or any issues in production. Because if we find bugs or the vulnerabilities in later stages, then it would be much more costly. If we find them in the early stages, then it would be easier and of course cheaper in terms of the effort which is needed to make the fix, or at least the system will not be down in production. So these kind of issues can be managed or avoided in the first place by having a good test coverage. So we should consider all different supported platforms, all the execution environments. So if we have any hardware or machines, operating systems, then we can try lots of different versions and lots of different platforms. Like we can test on desktop platforms as well, or on mobile platforms as well. So if we test only on desktop, maybe we may miss some issues which are raising only on mobile executions. Or if we are testing on only one of the browsers, then we may miss some other issues which may raise on the other browsers. So not to have any coverage issues, we can utilize lots of different test design techniques, like maybe boundary value analysis to consider all the corner cases or all the positive scenarios, negative scenarios, or we can do the exploratory testing to figure out what kind of other use cases there are, or we can use lots of different test design techniques. But eventually, we will have a good test coverage and we will have a good test input set as well. And after having all the design test cases, we can document them and we can build a traceability between the use cases, between the requirements and the test cases. And in this way, we can figure out what range or what rate of coverage we have, what rate of test coverage and the automation coverage we have, and we can figure out what kind of testability issues there are in the project or in the product. The testability issues I wanted to emphasize specifically because it is very important. There may be various reasons which are blocking us to be able to test all the aspects of the product. For example, if we have any instabilities for any reason, like if we are having some A/B testing activities and we are deploying some different versions onto our instances, then we may not know or we may not be sure which version we will hit when we are doing the testing activities, or the behavior itself may be conditional. When the user data falls into some specific range, then it will trigger some expected behaviors, but otherwise it will trigger some other expectations. So this kind of instances is a challenge to do our testing activities. Or if we have some hardware modules, it is really difficult to maintain the testing activities. At least the automation will be much more tricky, because manual testing maybe we can do somehow, but the automation will maybe require some simulation or the test harnesses. Or we may have some dependencies. If we are requesting or if we are pulling some data from other subsystems, and if they don't have some public APIs or some public interfaces, then some data is already lost in communication. For example, if I have to see only the items or the components having some specific IDs, and that ID, like the feed ID or any other IDs, is not visible to me, then I will not be able to do or check if all these components have this ID. So what we can do is, and what we did in our project is to go over all these kind of items and figure out what kind of testability issues we have. And then we performed another initiative and we tried to improve the testability. One activity was they implemented some interfaces, some APIs, public APIs, only for testing purposes, which will not be used by the end users, but just to improve the testability. The development team implemented some new APIs, and in this way, I was able to find the data or the attributes that I need to test normally, which normally I was not able to check. In the software testing lifecycle, after the tests are designed, the next thing is to execute test cases. And we can execute test cases either in manual ways or with an automated manner. So as we all know, today test automation is very important because most of us are doing continuous testing and we are integrating our test executions into our CI pipelines. Not to break anything, if we have any change or any update which is applied to our code bases, to repositories, then after each merge or before each commit, we run our test cases to be sure that these changes are not breaking anything. So to be able to do these continuous testing activities, test automation is very important. And in the meantime, it has lots of other benefits, like it is reducing the execution duration, it is reducing the manual effort, and sometimes it is opening the way for us for what we cannot do in manual ways, like load testing and concurrent request testing. Lots of different things we can do with the help of test automation. It is great. It has lots of different advantages, but it is not a silver bullet. It has lots of different challenges as well in the meantime. And we have to maintain the code very well, because otherwise it will be some other problems and issues. The code quality is very important. We have to maintain our test code in lots of different aspects. The reliability is very important, the robustness, the understandability, the maintainability, the reusability. These kind of aspects are different properties of the code quality. And for this, to improve the quality in our test framework, we need strong quality gates. Because if we let everything to be merged in our pipelines, then it means we are letting everything be in production. We are letting them go. So there are potential risks. They will raise some potential issues and problems. They will raise some trouble to us in our later workflows. And for this purpose, of course, the maintenance is very important, and maybe the peer reviews and some other static code analysis we can utilize. And one more thing that we have done to improve the maintainability with the help of the other development team members was improving the locators, because especially for UI automation, locating the elements on the web pages are very important. And so normally we use different selectors to do that. Like we can use the class names or we can use the expats of the elements. But sometimes if the web page design is updated by the development teams, then sometimes our test cases are broken. This is a very commonly known issue by the test automation engineers, and it is very challenging. So what we tried to do after an agreement with the development team members is use the common locators in all apps we are using, and we add some test data IDs. In this way, we don't have to deal with lots of different long and complex, complicated expats, but instead we just add the test data IDs, and even if the path or the ID or the class of the component is updated, the test data ID is still same, and our test case is not broken anymore after these changes. And one more thing is, of course, the reusability. The system that I'm testing, there are lots of different applications and the sites, but they have some common front-end and common backend libraries, common backend modules. So there are some use cases which can be tested on all these sites. Like they are all recruit sites, and users are going to navigate into these pages and can perform some search or perform some queries. Like they can put some different keywords or locations, and they can try to search some for related jobs. So this can be tested on all sites. So I don't have to write the same test case for each of these sites under test. So what I can do is, if somehow I can execute the same test case on multiple sites or applications, then it would improve the reusability, and it will eliminate the waste of time or maintenance efforts. So what I did is, I had to exclude all the environmental variables and the configurational settings apart from the test case itself. And then if I execute this test case with setting these variables from outside of the test case, then I can execute the same test case on different platforms, on different browsers, and on different sites. And in this way, we reduce the maintenance cost, because if one of the test cases should be updated, then now I don't have to go to lots of different classes, but instead I apply my changes on only a single source of truth. And I apply my updates only on the relevant test case, which are already executing on all the sites. And after the implementation, the next thing is, of course, to execute them on our pipelines. So to be able to execute lots of different suites or test sets, we had to decide about the priorities of the test cases, because accordingly we can define lots of different test suites, starting from the sanity set, and then we can have a basic suite or optional, and then eventually coverage set, and then eventually the optional set. So in this way, if we are running a regression test, maybe we can choose only the relevant test cases, or we can run only the sanity test, because after each regression run, it is not very feasible, and it doesn't make sense to run all the optional tests, but instead we can pick the relevant and the sanity tests to ensure there is nothing breaking anything in the functionality or in the working system, and we can improve the efficiency, because execution durations are very important. In each commit or in each merge request, if our test executions are taking too much time, then everyone will start complaining about it, right? So what we have to do is maybe selecting the proper subset. And to be able to do this, of course, the prioritization is very important. And what we did with the product managers and the development leads is to decide the priorities of the use cases and then the relevant test cases. So what we did is we created a matrix in which there are multiple dimensions of the features, like the visibility or the probability of the usage of these features. And on the other hand, the impact. If there is an issue on this feature, what will be the impact? How critical this issue will be? If the whole system will go down, or it will be only a cosmetic error, like the monitoring of some attributes or the dashboards on the UI pages, some text fields. These kind of features are maybe not that much critical, but maybe more visible to the end users. So deciding on these different dimensions, we finalized the priorities and we generated our test suites, and eventually we selected these suites on different jobs. For example, we have some nightly jobs on which we don't have any duration concern. So we can select a wider scope, but after each commit, which triggers our test executions, we are selecting a smaller subset and optimizing the test execution durations. And finally, last but not least, is the maintenance, which is the continuous improvement. Because when we complete all our activities, defining test cases, mapping them with features, implementing the test code, executing them, but when we come up with this point, then it doesn't mean that we can all stop our improvement activities, because we have to continuously maintain and we have to track the results. We have to understand if they are reliable and robust, because if they are flaky if they are failing from time to time, it will cause some analysis effort and maintenance effort. So what we have done is we generated open and public visible reports which can be analyzed by everyone in the team. And if we detect any flaky test, then we try to understand the root cause of the flakiness, and then we try to reduce this number. So I put two screenshots in this slide. The first one on the left is having some flaky results. It is a little bit difficult to read, but there are, I think, 7 or 8 flaky results in the same number of test executions. But on the right-hand side, after we applied our solutions, then we didn't have any flaky results in the same number of executions. So in this way, we reduced the maintenance and the analysis efforts to understand if the failures are the false alarms or the real bugs. And one more thing is, of course, continuously improve the testing durations. We can improve the test executions by reducing or eliminating the waste of time. For example, if we have some dummy weights in our test automation framework, we can remove them, or we can, if we have any redundant code which is not really needed to assert our expected conditions, then we can eliminate them and we can optimize the test executions. But additionally, the parallel runs are very important in terms of the automated test executions, because in this case, we don't have to wait for the whole suite to be executed at once, but we can generate smaller subsets, and after creating lots of different virtual machines, we can divide the whole set into these virtual machines, and we can do parallel runs. And in this way, we can optimize the test execution durations. In our project, we improved the efficiency, I think, more than 20 times, and we reduced the durations as much as possible. And not only the test results, but also lots of different metrics we can collect from the production environments. For example, some of them are related to the usage of the product or different features, and some of them related to the error codes that the users are getting. So if the product itself is not stable, and if sometimes it is going down and some services are not responsive, then we are collecting these kind of error codes, and we are trying to maintain the product and the resilience of the system continuously. So we went through lots of different stages. Those are all different rings of the whole chain, the whole software testing lifecycle. And in each of them, we can perform lots of different initiatives. But of course, this is a whole team effort. These are not some achievements which can be performed by individual efforts. So in each of them, the quality assurance members should work closely with some other members, and we should build a strong communication channel. We have to understand each other, and every process or every workflow should be very clear and understandable by everyone. For example, in clarifying the system aspects and the features, we have to work closely with the product managers. And then when designing test cases, we can figure out what kind of testability issues we have, and we can discuss with the development teams, and we can ask some additional interfaces which will be public to the testers, maybe only for the test activities, test purposes. But still, we may improve these kind of issues. And for test implementations and executions, we can generate priorities, and we can generate test suites, and we can apply some best practices to improve the quality of our test automation framework and improve the reliability. And eventually, by doing some monitoring activities, maybe with the help of SRE teams or maybe with the help of product teams, to figure out what kind of metrics are the best to represent our goals. These kind of initiatives we can perform and conduct to improve the quality in our products and in our processes as well. So this was the summary of all the journey that we have done in our teams to improve the quality, and I hope it was insightful. And if you have any questions, I will be more than glad to answer them. Thanks for listening, and enjoy the rest of the day.
All right. So we have time for a quick question or two. He's hopping on call, so let me just do that up. All right. Masood, can you hear us?
Yes, I can.
Okay, awesome. Yeah. So I guess, do we have any questions or thoughts, comments, anything? All right. Well, we don't really have any questions right now. If there are any questions, Masood is hanging out on Discord, so feel free to ask him on the channel there. And yeah, again, sorry for the technical issues. Hope you enjoyed the talk. Okay. Should I start? Oh, okay. Okay. Thank you, everyone, for being here. Sorry about the delay. There was a glitch in the previous session. Was remote, but I'm very glad to be here with you and be able to talk about one of the topics that I'm passionate about, and it's development as well as edge. So thank you for being here. It's going to be a kind of short session, around 30 minutes. So we will be doing some slides. I will try to show you a demo if the demo gods are with me today. So thank you very much for coming. Just a quick introduction. My name is Uko. I'm part of the Red Hat team. I'm a developer advocate focused on APIs, messaging, integration overall, and basically everything that is development related. I like to travel, food, history. I'm a Mexican based here in the area, so I'm local to the area. Not need to travel, and I have been doing development for more than 25 years now, going for every single piece of the software development life cycle. Um, I'm originally electronic systems engineer, so I did most of my majors in robotics, control, and things like that. We were doing machine vision when it was 2002, so it was very, very um, immature type of technology. But we're here and we're doing a lot of great things around edge, AI, ML, Java, and such. So we will be talking about edge computing and how is it related with the requirements of current organizations, companies, public sector trying to get applications, software, and these new capabilities all the way to the most remote locations. And this is because we need to enable computing and compute capabilities where they are needed. So it is perhaps a disaster zone where you need to deploy some servers and computing power there to spread insurance resources, or just to keep continuing providing services, perhaps during a cruise ship, or even in the International Space Station, where we needed to run software, do processing of data, as well as even just communications between Earth and the International Space Station. So this is why edge has become more relevant every single day. And when we're talking about edge computing, and at least from the perspective that I will be talking today, it's basically focused on these two characteristics. First, we're talking about the small servers. So today we won't be talking about devices and controllers and microcontrollers, because that's most of the times very kind of niche type of language and SDKs and specific configurations that are a little bit limited. So I call them more specialized. So in this case, where we're talking about more small servers, like an Intel NUC server, or limited servers regarding perhaps 2 cores, 1 core, perhaps 2 to 4 gigs of RAM. And then the other part is being available in a remote location. That means that some of those servers are not even connected to the internet, or if they're connected, they're over a unreliable network, or if it's possible, they're connected all the time, but that's the less of the occasions. So this is why we will talking about this. So as I was saying, no device edge, but edge that it's available on premise. Like imagine in your Dunkin' Donuts place, if you're from the area, you will know that there's a server there that needs to be running the point of sale. There's a one in any Chick-fil-A, or there's one in your car even, but those are more specialized. The other ones are from the telco providers. So in every 5G tower, there's equipment that it's running there. Some of them are already running things like Kubernetes over those servers. So those are the kind of things. And then more bigger data centers that are geographically distributed along different areas. So raise your hand if you're a developer. Okay. Raise your hand if you're an edge developer. Okay, cool, perfect. So we will be actually trying to address the requirements. So one of the things that I was saying is, when we're talking about the embedded systems, microcontrollers, ladder, assembly, and all those kind of things, are very kind of specialized and require certain more knowledge on the language. And this is basically because it is more like a low-level kind of language. There's not so many abstractions and APIs and frameworks on top of those. So you can certainly still learn a lot of these other things. There's a lot of people doing great, very interesting kind of applications with these languages. You have a Raspberry Pi and you have code some applications to that. It's very engaging. But in the case of this session, the following means we will talk more on the general purpose type of applications where you can use your actual knowledge from your background that is like let's say that most of the time cloud-based, and then we will be talking about those. So the my main proposal here is that if you have been doing if you have been doing development for cloud applications, for web applications, for servers on the cloud, AWS and Azure, or any kind of these environments, we can translate some of those cloud practices to the edge development. And when talking about the edge development, I'm talking about these kind of servers that we just talked about. So in this case, we can get all the benefits that we have been developing the last 20 years on the cloud, and then reuse some of this knowledge, some of this learning into edge development, and stop having edge development as a niche that it's almost like a cult where just a couple of people can get into. So we're talking about things that we have learned in the past, like CI/CD. So try to be able to deploy applications consistently and with quality. The benefit of container images. I was just talking yesterday with some folks that will be deploying, this smart advertisement on the streets, and they're thinking about containers because they will be able to upgrade and update and change the code running on those devices very easily. Other important thing to talk about is event-driven architecture. So we will be going a little bit on detail of why EDA is important and why with scenarios where you don't have a established connection that it's reliable, you need to rely on other kind of patterns to share data or just information and comments. We'll be talking about the new things on the old languages like native builds for Java, and also the importance of the hybrid cloud connectivity. So let's get started with one of the interesting things, and this is the one related to Java. So how many of you have been doing Java in the past? Okay, cool, perfect. You know Java. So most of the times when you say Java, and there's a lot of people bashing Java, it is because it used to be an impression from Java from 10, 15 years ago, where it was slow, it was heavyweight, and such. So this is how sometimes I see my code, right? So Java code, I'm trying to deploy that in my infrastructure, and it results that it is already overcrowded and mostly in the serverless train. But this is a very interesting thing, because when the race of Lambda and the serverless movement start, they require certain characteristics on the software and the development frameworks that will be running on serverless. So imagine we need to have cold starts, so we need to be able to easily start applications in less than a second. We need to be able to use less resources from CPU as well as memory, because we're going to pay for each one of those. So it is important to have a framework and way to deploy applications that are according with these characteristics. So Java was not doing that. And if you were doing Java, you remember, all things like WebSphere and other application services that took like 20 minutes to start. It was very painful, and that's why a lot of people move away from Java code. However, when the Java folks and the Java community start to rally and see that this is a problem, they start to do something. And one of the things that they start to do is these new microservices focused frameworks. And one of those, at least from our side within Red Hat, it's Quarkus. So Quarkus is one of the frameworks that allows us to have the possibility to deploy and create and develop applications using Java language, using Java enterprise frameworks, but at the same time being able to generate applications that are more serverless friendly, that are more lightweight in resources, in memory, in consumption, in such a way that we were able to reduce the amount of memory that is used by those applications, increase the startup time decrease the startup time to make it faster, as well as decrease the amount of this footprint. So in this case, you're able to easily transfer an application to a serverless provider and being able to deploy those. And the interesting thing here, and this is how we can take some knowledge from the cloud to edge development, is that those applications, while being originally targeted to be deployed on Lambda and serverless, result in applications that were easily deployable and friendly with low resource servers and constrained environments. So that means that if we take a limited amount of CPU from a Lambda slice and we translate that into a small device or a small server, it's almost the kind of same thing. So this is how we can translate all the benefits from what we did at the cloud with the evolution of a framework like Quarkus into edge development. And this is because we can not only create applications using Java language and being able to deploy those on a JVM, on a Java virtual machine, but also we are able to use that same application, use that same code without any further additions to your code base, and being able to create a native build for your target operating system. That can be a RHEL machine or a Linux machine, or even it can be a Mac OS or a Windows machine. And this is because we are leveraging some of the benefits of this project that is called GraalVM. So you have heard about GraalVM. It was a project target to be able to increase the capabilities of the Java virtual machine. Within Red Hat, we have been focusing heavily on the Java side, so that's why you see the ones in red. But one of the important things is this component called the Substrate VM. So Substrate VM, it's a reduced set of instructions from the Java virtual machine that can be embedded as an application. So in this case, when you have the traditional Java machine where you need to install a JDK or a Java runtime environment, with the Substrate VM embedded in your application, that's not a requirement anymore, because the VM that is executing your code, your Java code, your binaries, it is embedded over there. So we move from having an application server with an HTTP server that's independent from our application to embed the HTTP server on my code, and now we are able to embed the virtual machine that allows us to run our code anywhere in the same application. So that's the benefits of GraalVM. GraalVM it's a community project led by the same people that is leading the Java community. As part of Red Hat, we are very involved in the community. We are providing contributions around testing, support, flight recorder, and such. So now I'm going to show you how this is related. So let's go. I have here two container images. So one of the interesting things is we can either build our applications and create containers, and we can create containers using JVM and get the benefits of lightweight applications. Or also we can create containers that are based on our native builds and can be deployed like that. So if you're running on a server that allows you to run containers, like for example running a single node OpenShift or running a application or running a certain container manager like Microshift or single node OpenShift or even Podman or Docker, if you have a container, you get all the benefits of that, right? Portability and the possibility to update and such. Depending on how much management you need in your local server, in your edge computing server, you can define what kind of infrastructure you want to run. In my case, I have two images, and I will first show you the code so you can see. It is a very simple REST application. So if you can see on the left side, oh my God, sorry, you're not seeing my screen. My bad. Okay, so this is an application. If you can see, it's just a traditional Java application with a POM XML based in Maven. It has the code. It's basically Java code with annotations, CDI. You can use any kind of environments. And the benefit here is that this is just traditional code. This code can run on Lambda, can run on a traditional application server, or can just run on these native builds. So in this case, we have also the benefit of getting some Docker files that can help us create these Java-based machines. So we have this base image that has the Java development kit, and then we can deploy our application. But also we have this option that it's a Docker file that allows us to create a native build and then use the minimal image from the UBI 8 image on the registry from Red Hat, and then being able to deploy this application. So when you're working with these applications, it's sometimes easier to get this kind of deployment. So in the first part, I run the application that is running on the JVM. So you can see here, we have the information about the JVM run, and you can see that this server starts in less than 1 second, so around 0.8 seconds. That allows us to enable this service and running on port 8080. And this just returns the hello world message that I showed before. And this second one, it's a container image that is running my Quarkus application in native mode. So you don't see the code for the JVM anymore. And this application started instead of 0.8, that is, you will agree with me, pretty fast. It goes all the way to 0.025 seconds. So it is 20 milliseconds to start an application that it's running here on your computer. So I'm just gonna run this again. So you can see it start blazing fast. And if I want to just do a curl over this, it's rippling back the hello message. So it's an example of how you can reuse some of the code and some of your applications. Now, if we see the container image that is generated for this application, you will see that we have two applications. This one is in use, is the one that I'm running, so it's the native one, and this is the second one, that is the one based in the JVM, the Java Virtual Machine. If you see the difference in the size, it is pretty straightforward that it's almost a third of the size of a traditional image. So when we're talking about edge devices and needing to send these kind of containers over the network, it's a big difference sending half a gig for a container compared with 150 megabytes of the exact same application. So this is one of the benefits of using this kind of applications. But this is just a native image that is running on a container. But what happens if we are not running that into a container? So this is where we have the native build. So let me see. Let's open around here. Yeah, so if you see here on the target, so as we're saying, we're using Maven, so it's a traditional Maven target. And you can see that we can generate a simple jar file that is very lightweight, a fat jar that is including all the libraries under all the resources, and we can have this native build that it's a little bit more heavy, but this application, it's running with the embedded substrate machine. So if I run this application, I can just say target code with Quarkus and snapshot runner. So this application will run on my Mac machine in a native mode. Okay, so it's Didn't like that one. Okay, well, sorry about that. It didn't work. I think I replaced that with the Linux version. But this is basically a single file, a single binary. So this binary file, if you are running on a Linux machine that it's deployed on the edge, you can just copy that file. That you can see it's just 40 megs, uh, 42 megabytes, and you can just move that file system into your golden image, in your ISO image that is going to be configuring the service. So it's a very interesting way to get started with this kind of applications. So this is GraalVM, and as I was saying, we can generate depending on what type of container management you want to use. If you want to use containers, you can use Podman. You can use your native builds, your container images, and such. And the idea is also when you have no internet connection, you can do some things like event-driven architecture. So event-driven architecture allows you to implement patterns for delivering data when you have a disconnection between your service and those. And most of the most common ways to implement EDA, it's, for example, through events. So you have used Kafka in the past or any type of GMS broker or traditional message queues and topics. This is a way to implement patterns like store and forward, where you can process information, let these broker, these bosses, being able to take ownership of the message or the event, and then if there's a connection, being able to transfer that information all the way to the next stage. So in this case, when we're talking about EDA, we have things and benefits like a single node Kafka. So remember, if you're using Kafka on the cloud, you get all the benefits of these streaming application frameworks, streaming APIs, and reliability and scalability and such kind of things. But sometimes when you're on a device, yeah, you may got a lot of traffic because of telemetry and devices sending information into your server. But most of the time, what you want to do is really take the advantage of the streaming for that. So in this case, with the new developments in Kafka, we have things like this single node Kafka. It's basically it's the latest development in the Kafka community that allows us to have this server running, and this server is just one single container that it's running on the server. So if you see the container running, we only have one that's Kafka. So instead of having all these three zookeepers, all these three nodes, everything that requires a Kafka, you can have all the benefits of Kafka with just one single image that can run either as a container or as a JVM. And then you're able to execute on that service. So if I just access my local host 1992, I can see that there's one node broker that I can use. Obviously, you lose things like high availability and the possibility to spread across different partitions and replication. But instead, you get all the benefits of Kafka, so you can still use things like a Kafka Streams API and others. So now that's most of the things that I wanted to share with you, and there are other things that you can add. Camel extensions for Quarkus, so it's basically frameworks running on top of Quarkus that get all the benefit from that. We talk about the different types of OpenShift and Kubernetes that you can deploy on these kind of applications. When you're running on top of Kubernetes, you get all the benefits of things like operators that allows you to implement new development paradigms regarding function as a service, as well as all the benefits of serverless in your local system. So you can have Minishift being able to run a container that allows you to run snippets of code. So just to end the session and then perhaps open the floor for some questions. The idea is that we have been doing a lot of great things for targeting the cloud originally, But if you're a developer that have been doing application development in the cloud or web applications, your knowledge is still valuable, is still usable when developing edge applications. So you can create applications, leverage benefits of cloud native development. You can create and get applications that scale to zero using things like serverless locally with Knative and other benefits of Kubernetes. There are a lot of frameworks that you can reuse that are edge friendly, like the one that I mentioned on like Apache Camel, that it's embracing things like Quarkus and other kind of frameworks that allows you to run on this kind of new builds. And obviously the benefits of the data pipelines through EDA, like Apache Kafka or traditional GMS broker that we can see deployed everywhere in things like UPS and other type of carriers. So there's a lot of interesting things to do. I encourage you to join, for example, our developers site, so developers.redhat.com. There's a ton of content regarding how to use Quarkus, how to get started with the Kafka. You can use it either as a cloud service, or you can just download the binaries, run the containers as I did, and you can get started your journey in edge development. So thank you very much. I really appreciate this quick chat. And there's information on the Twitter handler if you want to follow me. Small, but sorry about the format. If not, I'm going to be there in the stand with the development program team. And if you have any questions, we can certainly address them there. If not, if you have something you can ask now, I think we still have a couple of minutes, right? Yeah, perfect. Any question, comment? Is this useful? Did I show you something that was not in your mind before? Okay, cool. Awesome. Who has tried Kafka yet? Have you tried, Kafka? Yeah? Quarkus? Okay, cool. Perfect. So now you can start blending them. Kafka is not still being able to run on top of Quarkus. I get all the benefits of these fast starts because it's basically a code that is like 10 years old, so it's very difficult to start to port all those kind of things. But the interesting thing is you can still run that in the container and then have Quarkus applications being able to consume and connect to that single node Kafka. So as you can see, there's a ton of things you can still do on this kind of edge development. So awesome. Thank you very much.
So, I just left the operating system.
Sorry, didn't mean to be in your way here. If there's,
Thank you.
yes.
Do you need to book time reminder?
That would probably be good. Also, oh crap, I need the Wi-Fi.
10 minutes, 5 minutes, is that okay?
Sure, that's perfect. Thank you very much. Why did I sign out?
Yeah.
try and snap over.
Yeah, right? Well, and of course, Google chooses right now to sign me out of. Google chose right now to sign me out of everything, so I have to re-log in. All right. Okay. Where is the mouse? Which way are you? Not that way. Are you this way? No, this way. Where did you choose to dump it? There we go. All right, and it's not going to give me anything here. Well, fair enough. That'll be fine. All right. We're going to go ahead and get going. So, good afternoon. My name is Eric Munson, and I'm here to talk to you about unikernel Linux. This is the subtitle is Applying Unikernel Optimizations to a General Purpose OS, or Ours Goes to 11. First, I want to say thank you to the unikernel team. So I'm on the list there down the second row, but that top row, without them, none of us would be here. They banged their head against this problem for a number of years to prove that it was possible to do what we're doing today. All right, so let's start talking a little bit about what a general purpose operating system is first. We're very familiar with these. They provide user separation and process separation so that every process running on an operating system can basically believe it has full control over that computer at all times. Modern deployments typically take a single user and segregate them into a virtual machine so that you have an entire kernel to yourself. But you still have all of that overhead of being a general purpose operating system and all of the separation of users that you still have to pay for, even if you're not actually using it. So what is a unikernel then? Well, the unikernel takes the idea that we're already deploying to a single application into a virtual machine. So why don't we take the kernel and instead of making it a general purpose thing that still interacts with processes as if there are multiple users, and link it all into the same execution context. We create a single binary that has application code and kernel code in a single unit. And then we execute that directly on the virtual machine monitor or hypervisor, right? So we've done away with a bunch of the costs of being a general purpose operating system, and we only keep what we need in the kernel right here, okay? So this has some really strong advantages. You reduce a bunch of overhead. Specifically, your system calls become function calls. You no longer need to trap to interact with the kernel. You now just call the kernel functions directly. You don't have to pay the overhead of process isolation, right? So that leads to things like you probably don't need a scheduler. You might need one for time sharing amongst your own threads, but you certainly don't need to aggressively make sure that everybody is given the same weight the way you would in a time sharing system with multiple users. You also get improved boot up times because you aren't paying for all of the subsystems you're not going to use. You're only going to configure subsystems you're actually going to interact with, right? And you don't need to actually initialize hardware. You punt all of that down to the hypervisor and make them handle the actual hardware bring up. And finally, you can end up with a really small binary at the end of it, right? You've taken your application code and only the kernel code you need and mushed it all into one. So it's likely to be significantly smaller than a general purpose operating system binary would be. But it comes with a cost. Nothing's free, right? There's no such thing as a free lunch. So oftentimes unikernels, they will claim mostly being POSIX compatible. None of them claim Linux compatibility. And even the ones that claim POSIX compatibility say that we will emulate the 80% of the POSIX API. And so your application is likely to work because whatever you need, we use, we emulate, we offer up. But they won't offer up the quirks that Linux had. So like the other side effects that you might expect from making system calls, they wouldn't happen. And if you need one of those system calls that's not in there, well, you get to write it yourself. The porting effort is really significant because of this, right? You have to ensure that the calls that you use are mimicked appropriately and they actually work particularly well. This is if you're lucky enough to stay within the language that you would pick for your application to actually build your unikernel. Sometimes they come with the overhead of saying you have to write everything in OCaml. Also, the porting effort can lead you to want to re-implement things instead of doing the effort of porting. So for instance, in the EBRT paper, they chose to re-implement the memcached API on top of EBRT instead of porting the code. So what you've done there is you've taken a production tested application and said, we're not going to use this code base. We're going to write our own. And I guess we hope that it's as good as the production one was. Unikernels don't typically boot from hardware. They require you to have a virtual machine monitor, right? And they do this because they don't want to have to deal with all of the mess that is trying to start up modern hardware and all of the quirks that come with working with BIOSes that are likely broken or buggy. They just want to punt all that to the hypervisor and move the code out and the complexity out of the unikernel as well. But you have to pay for the hypervisor. Runtime debugging. If you've ever logged into a system and tried to say strace or perf or ftrace or top or use one of these tools to debug what's going on in your system, if you don't have the notion of a process, you aren't doing that. It's not happening. And when we work with the Linux operating system, we get millions of CPU hours of production time. This is code that has been tested through whatever it is you want to throw at it. Somebody's done it on this code base already. That's not true of a from scratch unikernel implementation. Very few of them have any production time at all, and those that do, it's dwarfed by the fact by Linux's production time. So there was a lot of work put into making Linux into being able to use it as a unikernel. And Ali and, as I said, Ali and Tommy put a bunch of that effort in and made it happen. But towards the end, they started deciding, well, are we asking the right question, right? Do we really want you to have to choose between a general purpose operating system and a unikernel and make that a binary choice? Or would we kind of prefer to have something a little bit more analog, someplace where we could pick and choose the bits of unikernelness that we actually want to use for our project, as opposed to saying it's on or it's off? Well, that led to a couple of design priorities when actually doing the UKL implementation. And these design priorities, they are, we want to maintain as wide an application support as we possibly can. We don't want to force you to re-implement everything in OCaml. We don't want to give you parts of the API. We want to give you the whole thing. And we don't want you to have to re-implement everything depending on what we have provided. A big one here is Linux's HCL is huge. Modern applications don't just use a CPU and memory anymore. They're going to be touching things like storage arrays or GPUs or TPUs on the side. And if you don't support those in your unikernel, you're not going to be working with these modern applications. And we want to keep Linux's HCL, so it's good to just, if it's already there, go ahead and make use of it. And finally, there's a wide ecosystem of things that come with supporting Linux, including a huge development community. So somebody out there knows the subsystem you're having trouble with, whatever that subsystem is. It can probably help you fix it if you need it. There is a rich set of tools and libraries already built on top of Linux, and we don't want to throw any of that away. And finally, those debugging tools I mentioned, no sysadmin is going to stay working for your company if you tell them they can't use any of those tools to debug production problems. So with that, we come up with the UKL base idea. This is the base configuration supported by UKL. Now you'll notice a couple of things. First of all, we have the application marked with actually linked with the kernel, as we did in the other unikernel illustration. However, you'll notice that in the previous one, that standard C library wasn't there anymore. But here it is. We maintain compatibility with glibc, and so the interfaces you're used to working with are still there and still usable. And finally, we don't discard the notion of the process. In UKL base, you are still allowed to start unprivileged user space processes to do whatever they would normally. So you want to bring up the network? Fine, you can do that. You want to start systemd? Great, you can go ahead and do that too. File system mounting? Not a problem. All of that can still happen while you have your privileged application running in kernel space. Now, once we have this base model working, this allows us to explore a couple of unikernel specific optimizations. And the four that we looked at for the paper are bypassing kernel and entry exit code, avoiding stack switching, using ret instead of iret for all transitions from kernel space to user space, and then applications interacting with the kernel directly as opposed to through the system call interface. For this talk, we're only going to talk about the first and the last. And I know they sound similar, but they are very different in what they require from the developer to actually implement. So first, an explanation of bypassing entry exit. I know there's a lot here. Just know that the call chain is long. And we get from, this is the call your user space process made, read, down to doing the actual work of TCP receive message. The stuff in the middle, just know there's a lot of boxes. Okay, so when you make a system call and you transition in, the kernel does several things before actually dispatching the system call to the thing you've actually made. It does things like checking to see if you need to call the scheduler, checking to see if there's any pending signals, doing RCU epoch handling, and a number of other bookkeeping tasks as well. However, these bookkeeping tasks don't need to happen on every transition. You check to see if they need to happen, but you don't necessarily do work. So with our bypass technique, we look something more like this, where read calls directly to ksysread, skipping the bookkeeping work. Now, it's not quite like that, because remember, we wanted to maintain 100% compatibility. So this actually happens as a combination between the libglibc and the kernel itself, but it doesn't require the user to make any changes to their code base whatsoever. You can control the frequency of this skip, but we'll talk about that in just a second. Okay, so that was nifty. It didn't require any code changes from the user, and we got, potentially some performance benefit. Now, for the deeper optimization, for one that requires more user input, more developer input on this, we talked about calling directly into kernel functions. So in that call chain, which we'll get back to in a second, there are 6 or 8 functions in the middle that are just disambiguation. They're getting from the fact that the read and the write system calls support the notion that everything is a file or a file descriptor, and underneath it we'll decide, well, what kind of file descriptor is this? What kind of socket is this, et cetera, as we get down to the actual code that's going to do the work. If we know a priori what this write call is going to resolve to, why not just call it directly? Just skip all of the middlemen and just go directly. Now, it's not quite that simple. Sure, you have to transform from the file descriptor you had to the sock struct or the IOVEX or whatever it is you need to do, but you certainly can skip most of that intermediate code. So you left with our same call graph for read here, and instead of our blue, which jumps a little bit, we jump all the way down into calling TCP receive message instead of calling read, right? Which can lead to a real significant savings. So let's look at some benchmark results. So for this graph, we have taken a benchmark called LEbench, which is really just made to measure how long it takes to execute a system call, and integrated it with UKL in 3 different, with 2 flavors, and run on a baseline. Now, the 3 setups we ran are straight Linux, UKL just linked the application into the kernel, and finally we turned on the bypassing that I talked about at first. So this is the skipping the entry exit bookkeeping code for 9 out of 10 system call interactions, right? And so you'll see that just by linking the application, we see a modest improvement in performance, right? And these are average system call times just to make that one system call. But when we get to actually doing the bypass and we're skipping those checks, now we're not skipping it entirely, we're only skipping it for 9 out of 10 interactions, we see a huge performance improvement in all of these system calls. But the real magic, and we'll get to this in a second, is actually reaching deep into the kernel. So this is a complicated graph. This is going to be talking about running Redis on Linux, on UKL bypass, and then also on the shortcutting. But what you need to take away from this are these 2 numbers. These are the 2 numbers that we care about. They are the average or P50 latency for a request and the P99 or the 99th percentile latency, right? So we see we have about 2 milliseconds and about 3¼ milliseconds on Linux baseline. When we just link Redis in and then turn on our bypassing, we see about a 10% improvement in both of those. So a 10% reduction in average and a 10% reduction in P99 as well. But when we decide to reach in and call those TCP functions directly, we see 23% improvement in the P50 latency and a 22% improvement in the P99. And the other real win that needs to be called out here is you'll notice that with each of these optimizations, the distance between those 2 numbers has shrunk. So we are cutting down on the window of latencies that you will expect to see when run with this setup. We also ran memcached with a number of the same setups, the Linux baseline, the UKL linkage, the bypass, and the shortcut, and we see similar improvements along that spectrum, right? With bypass and shortcut showing really significant improvements in the number of queries we could satisfy under our 0.5 millisecond SLA. Okay, so we talked about ours goes to 11. So let's get to the actual going to 11 bit. So secrecy is a multi-party computation application developed here at BU. But the key thing we need to know for our work is that it does a little bit of processing and exchange a very small TCP message at every round of processing, right? So it does a lot of very small traffic, right? Which is normally actually really hard on Linux because you bump into all kinds of things like congestion control and then whether or not you're awake and can receive the interrupts when they come in with data, et cetera. So we took this and we ran it with 3 setups. We ran Linux, the baseline, the bypass, and the shortcut, okay? Now, Linux performed okay. They were, but the operator that we chose to test had been sidelined by the secrecy group because it said it's too slow. We can't actually use this in query planning because no one's going to rely on what we got out of this, right? Now, for 100 rows, which is not really all that big, we saw a really good improvement for the bypass, but we started to come up to the other things that we'd expected to see, anywhere between 25 and 18%, or 18 to 25% of improvement for the bypass. However, with the shortcut, we didn't just see a few percentage points. We saw a 95 times reduction in runtime, right? Now, this sounded crazy. Like, no way, that's not real. 95x, that's not a thing you could actually see. So we did some investigation. And we first noted that we didn't drop any TCP packets. The same number of messages were exchanged in the baseline Linux run as well as in the shortcut run. But we did notice a dramatic reduction in the number of interrupts being generated by the NIC, right? And what we came to find was that because we were moving along at such a rapid pace and never scheduling, the NIC never got a chance to get out of polling mode. So it would stay and just feed data to us as we came back. It was ready, you go ahead and take it. No need to put the application to sleep and then wake back up again when there was data available. So we skipped paying the cost of all of that and just ran to completion effectively. Okay, so what's next? The UKL project is going to be, so we're currently working on getting the patches ready to be posted for upstream. We hope to do that within a month or 6 weeks. It's taken some beating, and we're going to have some people to convince, definitely. But we're ready to do that. And we think 2 weeks. Okay, my advisor says 2 weeks, so 2 weeks. But some of the more interesting work that we have here is like, now that we have this result with secrecy, how can we go even further? Right? Can we make use of memory management within the kernel instead of using keeping the user space arenas and malloc involved? Can we just call vmalloc directly? Right? We're looking at event-driven applications. So that's very generic. Let's talk a little bit more specifically. The kernel in its nature is an event-driven application. Things happen, the kernel responds to it, right? It doesn't do things unless it's been told to. It just sits idle otherwise. Now, many applications for infrastructure are written the same way. However, because we present this notion of you're just running on a VAX, and there's this impedance matching between kernel events and user space events that goes through the threading and the scheduler. But what if we took that out, right? How could we improve the performance of these event-driven applications by tying them directly into the event interface of the kernel, as opposed to having to go through the C layer? We're looking at accelerating container deployments. Specifically, we're interested in talking with the Kata containers folks about how we might integrate that with UKL. And finally, we're also looking at interpreted language runtimes. So for this specifically, we were looking at JavaScript and WebSM, but we're also interested in Python because we feel like these might be interesting notions for things like serverless deployments. All right, well, thanks very much for coming out. Now, do we have any questions?
I know you said containers is like a future development thing.
Sure.
What about Kubernetes in general, and what about OpenShift, etc.?
So I haven't done any looking into it, but we're open to talking to anyone that wants to talk.
Yeah, so I think that this notion of Kata containers seems like a really cool match for this. If you want to do the base environment, I'm not sure. I can't. The one thing that I think Eric didn't talk about is that there may be able to be the notion of, like, this is just generically the ability now to mix application code with the kernel. You know, do we need fused file systems? That might be a beautiful way that we could accelerate that because now we have the ability to write application code that actually is directly in ring 0. And so there's a bunch of things we could do, but we're really eager to work with groups that have uses for this.
Okay. 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 Okay, thank you. Thank you.
What is the current level of like extensibility in terms of what different types of applications can be compiled into UKL today?
That's a great question. So we have worked with, obviously we worked with secrecy. We ran the benchmarking tests. We have gotten Nginx running. We've done DNS mask. We're also looking at So we're looking at talking to the Ceph Rados group about doing theirs. But there's effort to get it working with UKL, but it's not as drastic as re-implementation.
I think there's no effort to get it, like UKL just runs regular applications without change. Then you can, the point is, it's not like you can sort of start it and then you can, and then the idea of taking an application, statically linking it into the kernel,
right?
That's the part where.
So the point I tried to make with the calling out the two different optimizations that we covered was that you get the baseline and it's really very little effort for a developer, right? There's some relinking, some recompilation and relinking you have to do, and then you've got it, right? But if you want to reach deeper, you can put as much effort into going fast as you want, especially now that you have access to kernel internals. You're not limited by the API presented to user space. You call whatever you want. Yeah, so this is an idea that the team has kicked around about adding entry points that would easily take the same APIs presented in user space, but do the shortcutting for you for things like TCP connections. Yeah.
You said in the presentation that you currently need a hypervisor.
We don't. We boot bare metal. Right. If Linux supports it, we still support it as well. So if you want to bring in up bare metal, most of the testing for this talk was done on bare metal machines, right? But it also can work with a hypervisor.
Okay. Right. So how does this translate to embedded environment? Have you tested them?
No. But I think it would actually be a very interesting test bed, right? Because you care about all of the things that unikernel can provide, right? Yeah.
So I think one really fun part, not about embedded as such, but it's actually real time. What this gives you a lot, like we found that just it's naturally more deterministic. It's easier to control those things. Plus, as an application now, you, for example, have direct access to RCU capabilities like that. So we think that that's going to be one of the potential gains, is to allow all the Linux code base, but now being able to have an application that's actually got more deterministic response, and that's why.
So to talk about this a little bit in more depth, the error bars on this graph are the coefficient of variation for the runs, right? And so you'll notice that as we apply UKL techniques, they get there's some variation in the very small ones, but the Linux variation is giant compared to either of the UKL ones. So you are paying significantly less in jitter and for every call that you end up making. It's much more deterministic in how long it's going to take. No, we currently only support x86 64, but I mean, especially once that we get upstream, we hope that effort will look much like the KVM effort did, right? KVM got upstream for x86 only at first, and then branched out into Power and ARM. So we hope to follow much the same path.
Have you done course that actually specifically leverage GPU hardware?
So we looked into it for the paper, and unfortunately, a bunch of the OpenCL stuff still requires proprietary dynamically loaded libraries, which are not something we support. We have to at least be able to recompile the code and relink it, right? And so we couldn't get NVIDIA or AMD to turn over those libraries to us. So I don't know if anybody's got an in there. We'd be happy to talk to them.
Well,
But
just for clarity, we didn't ask them to do that. We asked them to statically link them.
Right.
And so they wouldn't have to release that either, but if I could just recompile them in a way we provide.
Right. No, we're not asking them to change their open source policy and release all this, but just a relink and providing us with a static object we could use. And so far, they haven't taken us up on it.
That would be huge.
Yeah.
That would be huge.
If you know somebody that could do that.
I will reach out to you. I might know a guy.
Perfect.
Yeah, I mean, we could even give them an experiment to run where they
certainly.
So even if they won't give it to us, but that would be. We'd really like to be able to demonstrate this work.
Right, because theoretically it's all there, right? It's just we haven't actually verified the GPUs are a functioning thing yet. Yep.
I'm fast forwarding into the future.
Okay.
This is in the past. It's already done. It's successfully available in production for most people 5 years. where do you see this going on AWS and on public cloud?
So that was actually one of my motivating, like, why is this work cool and why I wanted to join this lab, was that most of the AWS stuff is exactly this kind of deployment. It's one application you care about, perhaps with some supporting user space, but generally it's one thing that you're doing, right? And I could easily see this being the way that people choose to deploy that one application, right?
If you're a DBaaS or you're a SaaS or whatever, you're deploying on AWS,
Mm.
it would be kind of sweet.
Indeed, yeah. All right, do we have any other questions? Fantastic. All right, well, thank you all very much.
You exceeded expectations.
Oh, well, thank you.
Well done.
Thank you.
Sorry, we.
No, it's okay. No, it's okay.
Are you gonna have audio on your? Are you gonna have audio in your presentation, like videos playing? Or no?
No.
If you do, you have the box over here.
Okay, sure.
But we
Thank you so much. Yeah.
This is the mic. And there's a lab here too, if you just wanted to walk around. Testing.
I just like set up here, but do you need time reminder? Okay, thanks. Okay, should we start? Should I start? Okay, welcome everyone. Thanks for coming to our session. So my name is Uğur, and here is Amin. We're going to present you today cooperative caching for object storage. This is a project. We have a large team actually. We are students from researchers from Boston University Northeastern, and we are also collaborating on this project with Red Hat folks with the Ceph team. So data centers like typically have some form of like hierarchical network, and as and bandwidth gets constrained as the communication has to traverse higher levels in the topology. The massive like demand of data today, as a result of massive demand for data today, data centers create a single shared immutable data lakes. And these data lakes designed to store all the data for all the clusters running in the data center. And they efficiently store the data running on high capacity and slow disks. So this like popular architecture, single shared data lake, can result in like poor performance. Then all the clusters, compute clusters, access the data lake over the very limited like bisectional bandwidths, they see performance degradations. Also, these data lakes like typically designed for or optimized for particular access pattern, but today we know that there's like different applications with very diverse demands. They're all share these data lakes. And finally, as I mentioned, they run on like high capacity but slow disks. So compute clusters like frameworks or cluster resolve this issue by deploying caching. And these caches are great because they bring locality, they cache the data. However, they have two problems. The first one is they don't allow efficient sharing. So if both cluster access the same data, we have to redundantly cache this data on these expensive cache resources. And in today's like virtual environment, the clusters like grow and shrink, grow and like shrink to match the demand of applications. And if we have, for example, a dirty data on one of the caches, let's assume we have a 1 terabyte of dirty data, it takes tens of seconds to write that data back to the data lake before releasing that dedicated cache resources. So like in 90s, early 90s, like 2000s, there was this idea of cooperative caching, which is like initially designed for distributed file systems to extend the file system across the machines that access it. So rather than like deploying cluster or framework caching, basically in our research, we explore, can we use the same techniques to extend the data lake over the data center? So we implement or we design two cache architecture called D3 and D4N. And basically what we did is we distribute SSDs all around, and both design like we distribute SSDs all around the data center and form a cooperative caching. So this design naturally caching the data on the access side of bottlenecks, so we provide locality. It's naturally support sharing because if somebody already brings the data to the cache, remaining clusters can access the same data, so we are not wasting any expensive cache resources. And also, because these caches are not dedicated or siloed to particular cluster, we can naturally like support cluster elasticity. So we integrate both of our design in the Ceph data lake. And Ceph provides a piece of software called Rados Gateway. And Rados Gateway is basically provides an S3 API for users or applications so user can access the object store. And what we did is we take this Rados Gateway and explore, can we integrate the caching functionality in it? And then we can distribute this Rados Gateways all around the data center and form the cooperative cache. So when we like start this project, we were try to like explore, can we integrate this caching into the Rados Gateway? Because Rados Gateway is not designed for doing caching, it's designed for something else. And we want to make sure we don't introduce any major changes to the code. We want to make sure we don't make any changes to the existing flow. And obviously we also want to make sure, is this gonna like perform well? So we come up with a very clean design. Basically, we avoid to maintain any global state. We go with a multi-layer architecture like a CPU caches. So we have a layer 1 cache local to your rack, layer 2 local to your cluster, and we have a layer 3 which is like shared across the entire data center. And we use consistent hashing to locate the blocks on the higher levels, and we avoid any maintaining any global state. And the D3N also only supports non-durable write cache. So with this like clean design and thanks to the Red Hat Ceph engineers, we were able to like upstream the code. And by running a lot of experiments, we also showed that actually our implementation was super fast. It was able to saturate the like maximum speed of SSDs and NIC. And we also run like some real workloads. We run a trace from Facebook MapReduce cluster. And we showed that like D3N can improve the performance of workloads up to 3 times. It can reduce the reduction on the data lake by 4 times. And then the next obvious question, all right, now we have the D3N, and can we now, for example, support write requests? Because there are a lot of like intermediate data sets. It doesn't have to go all the way to the data lake. Can we like keep those data sets, make sure they live and die in the cache? And can we also support wide range of applications? Because applications have, for example, serverless applications access like in small granularity, big data applications access the data in much larger granularity. So in D4N, we design a resilient distributed directory which maintain the global state. And we also provide a durable write tier. So instead of like implementing the write tier from scratch, what we did is we take the existing Ceph OSD code implementation and deploy it as a write tier and layer on top of to the data lake. So this way, we were able to replicate the data redundantly, either using erasure coding or replication on the write tier. We were able to use the global state in the directory, and we implement a novel algorithm where we can able to compare the value of block in each different cache. And as a result, we see significant performance improvements. So we run the same Facebook MapReduce trace, and in here you see we compare the D4N with D3N, also with the existing state-of-art solution, which is Alexio. And these like yellow and red bars are Alexio with 2 different configurations. And the performance improvements of D4N come from 2 things. First, it's doing write tier with erasure coding, which supports writes and provide very high throughput. The second performance improvements come from the novel algorithm that we use, but which exploit the information that we store in the global directory. So D3N, as I mentioned, is already upstream, so you can access it. It's on the there's already documentation page on the Ceph web page, and right now we are on the process of upstreaming D4N, and we are trying to integrate the D4N with the RGW's new feature called Zipper. So hopefully it will be available to everyone's or broader community soon. But yeah.
So as Ur explained, D3N and D4N are storage side caches. And this puts us in a unique position. We have access to a deep sea of information like global state through directory. We have past and current access patterns. We have also information about environment. Where is the data? Where is physical location of the data? Network bandwidth usage, and all those information. But before we get to how to exploit this information, we should consider one important thing, that we are out of cluster now, and we are losing some information that we can get from clusters, like information from users, frameworks, schedulers. So the question is, can we make it up for it? Turns out we can. We developed Quarkus, which is a caching mechanism for analytical frameworks. As we know, analytical jobs like Spark job consist of graphs of tasks. These graphs or DAGs show what data is going to be accessed in the future and what is their dependency. Quarkus extracts these DAGs from the scheduler, and through a simple API, asks D4N to pin the data that is already in the cache and prefetch the data that is going to be accessed in the future. We compared Quarkus with 2 state-of-the-art caching policies for analytical frameworks, MRD and CP. CMR is our main Quarkus algorithm. And we ran TPCH queries on a data set we inspired by a trace we got from an industrial collaborator. And as we can see, in different types of queries, seeing ad hoc, linear, star, all the different kinds of queries, Quarkus gets better performance. So now that we solved that problem, the question is, how can we exploit the storage side information? First of all, when a cluster is shut down, it loses ability and resources to keep the information of its access patterns. But as a storage side cache, we can keep this information. We can store the metadata along objects, and we can have this information from creating an object until the current time. So that's a huge opportunity for us. We can design informed caching policies. For example, for serverless frameworks, we know that there are a lot of small writes. So we can use a coalescing to make a big write, one big write instead of small writes, several small writes, and get better performances. We also can develop intelligent algorithms. We can, as I said, we can have past information. So we can know what data will be accessed in what time of the day. So instead of having a passive algorithm like LRU, we can have active algorithms that knows what data should be cached or prefetched into the cache. And these are all not old theory. D3N, D4N, CARIs all are developed and deployed on MOC's MOC Alliance's infrastructure. We have 50 petabytes of storage, thousands of servers, and all of them are running on MGHVCC, which is a data center. So it is real. As Ur explained, D3N is upstream, D4N is getting upstreamed. So you can get information for these projects through these links, and we are here for if you want to discuss more about these projects. Thank you.
Thank you.
So the other cool thing is I think we're going to layer both these together. So hopefully we get D3N as, so when Eric was talking about the unikernel stuff, right? All RGW is a server is running event requests, right? We think we can actually get this all running on UKL as an optimized server because it's just, especially when it's going to the SSDs, the performance is going to be really critical. So, you know, it's a really natural target because this thing is doing very fast operations to local SSDs as a result of tons and tons of requests coming in over the network. So these projects kind of tie together.
I was wondering if I may be misunderstanding you, but you're talking about basically doing like actual sort of object store caching. Does it impact? Can it impact like query planning? Like just take an example of Spark's Catalyst query planner.
I mean, right now that's what we are trying to do. We can trying to exploit the existing information stored in the directory for schedulers in the like Spark or Hadoop, so they can maybe rearrange their scheduling or query planning. If you know if there's already existing data cache data, so maybe they can prioritize those queries or tasks. So that's our like kind of the one of the directions that we want to go.
Actually, I mean, it'd be really cool if there's people that work on those because it can go both directions, right? Is that if you know what's in the cache right now, then you can design your query to actually optimize for that. Right now, we're only going in one direction. We're extracting the DAG of what decisions it's already made about the stuff, so we have a small visibility into the future. Caching is way easier when you know the future. So we have the small visibility of the future, and that's the advantage of these guys. But actually, it can go both directions, right? If we can, if there's some people that really understand how the scheduler works inside Spark, then exposing what is cached and where it's cached is going to
yeah.
I've done some modest work with Camel, but the interesting thing about it is it's pluggable. You can actually write custom scheduling stuff.
Well, you didn't take this a step further. I think part where we're hitting a wall of we don't really understand how this stuff works is that there's Spark on top of OpenShift, right? And as far as I understand it, like OpenShift just obscures physical locality at all, right? So then we have the question is how do we know what's close to us, which cache is close to us? How can we, so we're working on the storage side, we know where the rack requests are coming from, we know the racks, we can cache things, but if you now want to schedule something, well, you'd like to schedule it on a rack, which already has the data cached, right? You'd like to, on the other side, be able to prefetch the data into a cache near where the thing's going to be scheduled if it's definitely going to be scheduled. So locality is being totally ignored today in the way OpenShift works, in the way Spark works. The only locality they're taking into account is per machine locality. And at least in our data center, there's limited bisection bandwidth outside of that, locality is really important on a rack level or inside a group of racks that are co-located. So figuring out how to slide this information, one of the things that Peter, some of our collaborators will be doing at Microsoft is actually passing hints between layers rather than just making explicit decisions, sort of saying, this is a hint on a color on where to actually execute things. What's the right interface to expose that locality? It's just,
yeah,
I think really excited though.
Yeah, in like today's people doesn't go and just stay in one environment. Like they open computation on different regions, different cloud providers, and and I think this is like a little bit hard problem. Like, should we prefetch the data, and if we're gonna prefetch it, can we prefetch from maybe other caches that sits on other region rather than backend, or should we ship the compute? So I think that's an interesting area that all of us also want to work and explore more. Yeah.
So it's just sort of putting in the broader picture. I think if you look right now, Alexia, things like that are just in these cluster caches, right? They don't have visibility anything outside of that. And that's what we were saying at the beginning. We're sort of at the data center level of stuff. We have storage. We can actually have the physical locations and stuff and see things across them. And then some of the colleagues we're working with, for example, at 2 Sigma, they have these really complicated workflows where they actually pull data in from the market at a certain time. There's a well-defined time where that data is going to be processed, or everybody's now going to access this data set later on, right? So all this stuff's invisible if you kind of introduce caches within the clusters. Yeah. And like one of the things that Mean pointed to is looking at the history. We analyzed the traces that came out of IBM. There is very, very repeatable behaviors that happen over large timescales, that everybody's ignoring right now. We're just catching things with sort of LRU or OQDA and stuff. And when in fact at a data center level, there's these real workflows where something creates something at a certain time, it's processed by a bunch of things the next day, and like massive amounts of the data access are going through predictable workflows.
Yeah, a lot of these show cron tab behavior.
Thank you.
Thank you.
What's that? Oh, kernel developers. Yeah, no. Really great. I mean, and actually, Peter, he's actually on sabbatical. He's my conspirator crime on the whole storage stuff. But he's actually another kernel guy. He's done way more of it than I have. I've written more exotic kernels on hypervisor stuff. So yeah, no, I mean, it's great. Because I kind of done the course for development and stuff. Yeah. Yeah, so it'd be great to get. Oh, I can show you sort of where we're at. It really sucks right now, but I've committed to getting this done before January. So, yeah, we're basically we have all the lectures we did in the last 4 years, so I'm just going to take those, convert them, and then start adding material. I mean, I hate working for other people's textbooks. They don't know. But writing this is. Do you want me to show you what we've done so far? It's really in its infancy. Most of the time, it's spent so far.
Yeah. So this, I did. Like kind of. I mean, so unofficially, right? There's this professor who was he's like, well, I'll be involved in the semester a little more, and then he disappears until the end. He's like, oh, you fine, whatever. So
So basically, I just wanted this is stuff that why are we doing this? Why are we doing open source application stuff? And started just putting various bits and pieces, like so I'm just. But the next part of this, this is so cool. I can write a little piece of code in this, which is LS. So I can tell them like this is the process, and these are the stand in, stand out, and stand there, right? So it's integrating kind of code with the checklist. So this is the static notation, and then if you go to, but you can look this button right now is actually going to operate first, which is the right place out. Click on this, then yes, that will then go into it and directly have access to that. That's what results from how we did it. But basically, every student gets their own container. I'm not going to try to do this really but yes, it shoves that into it. What we're going to do is sort of the textbook itself may will be sort of richly linked, sort of, but mostly static. But the code in it, like the specific example is going to be copying and pasting by running the textbook, right? Or running that page. Then the dynamic content is sort of lab manuals and stuff, which would be totally dynamic and interact with it, with sort of shells embedded in it and stuff like that. And then there's the small, which is working out the right strategy. So I think I've outlined what I want to do right now. I think we can use that but mostly I'm trying to stick with what we're talking about. Yeah. So I think basically what we're trying to just write down the core sections of Besides the loop synchronization, so you spend about 30 plus minutes to master those things. I've always done it before, but I'm realizing that's the part that's building that. I can teach the synchronization. That's how you describe our scenario. The problem too is that I can't really describe synchronization until I introduced enough about multiplexity. Like, if you look at the way Camel and other books describe synchronization, it's all about concurrency, right? And to me, but the point is, yeah. So if you're dealing with single processes, right? That you can do monitoring, you can all kinds of techniques. The big kernel lock is just fine. We broke all those things, and that's not because there was more concurrency, it's because there was countless, multiple cores. Yeah. So we have, you mean someone talking layer from that to another layer. Someone talking to another. All synchronization is because we embed locks in the data structures. Right? We don't, in fact, but it's
Oh. Oh, awesome. Thank you.
Yeah, we'll be floating around when it actually kicks off.
Yeah. And do I have to be mic'd up or do I just speak into this?
This one here, if you're primarily going to be standing here, but we also have a clip on that if you want to
Okay.
wander around a little bit.
Yeah, I might do that. I saw people were just like holding it up like this.
Yeah,
Yeah.
you can,
Okay.
you can unclip it here.
All right.
This should rotate, so if
All right.
you want, you can just hold it.
Sounds good. Thank you.
And then I'll have an off switch on the top if by chance we're not here.
Yep.
These are yeah, it is. Yeah, that's common. I don't know this. I don't know the so no, I just summertime. It is, yeah, it is. We'll see what I feel. Yeah. But I've seen. Yeah. 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 Sometimes I will enjoy. Yeah, yeah, let's go. Hey, how are you? Good. How are you? Good. Sorry, I lost it. I have one if you want. Let's start. Right. Something else. Until not a week or so, you know, you described it to me once. You have a bunch of choices. I should do it. Too much. But we had two cars. Regular cars. Now you're on the part of This is a couple of minutes. This is my favorite video. You'll see why. She's just so. She wants to do cracker things. She's just starting. This. She's a lot. They change so fast. She's just so cute. We really enjoyed. She. We were over there the other day. She has this. Plastic.
Oh, and it has the capture?
In the bottom. So we were over there the other, one of the, a little while ago, and she's really good. She's just tiny. One year old. She's on our anyway, so we're over there. We fed her. Her mother's. My son. They have a bunch of aggressive mouth. So we went over to watch her. We fed her dinner. She had a whole thing of squash, a whole thing of turkey, a whole thing of steak pieces, cheese, cut it up in pieces, ate all that, ate a whole banana, and then even she's also she's gone some of the times. Anyway, then she wants me to take away the tray. I take away the tray, and she goes, it's just so funniest thing. You just have to be there to see something, just appreciate how funny it just as innocent as can be, and they do nothing at all. This is one of the mountains that they're probably 50 minutes away, and we close enough that you can go visit if you want. Oh, we do at least 2 times a week. We sold a house that was about one half. And I said to my wife, this doesn't work out. You have 2 sons. One are in childhood. The other one was getting married. And I'll talk to you later. So now they get married next spring. And so it's this thing. At that age, all your friends have them all the same. Say, we have 2. And then once you have 1, you have 2. It's really complicated. At that time, we'll stop the evaluation closer, and we are, we'll sell this house. We sold the house. The house is big. So we sold that. Someday, a nicer. Well, it doesn't matter. We believe it. So we'll see what happens. We're in the stage where we're like, okay, we need to start getting rid of some of what we know. Eventually, they're probably not doing something. We're going to want to do it. So what? So we have, like, we're expecting California. I don't expect anything like that. This one has the only thing. But anyways, then we were looking at projects, and our youngest guy did the same thing. We called it and so the cool kids did all these kids. The one that went to Colorado, one of them. You got the second. You're doing something. Well, you'll do what these girls were all the same. We were in our but I guess I'm older. Anyways, they did all these But anyways, when you were it was a more extensive program. Anyways, then they get picked up and put it away. And then what? She was there. And if you know about it, and a few times that he called me, for instance, one time he called me and said, Dad, because it's getting killed out, because it's in the ocean. So he said, just be careful. But he called him on the way back. He said, Dad, you know, something like you said before, this is but not he has hope for the best. Never just like I said, life is full. Anyways, so they're oh, we were talking about. So we can go to we don't know water. It was a nice, a real big. It only comes as we wanted to do much more, but this I want to take which I did. So yeah, just go. So in this particular case, hard to so we do get a good sense of the work. They get it. It's going to do it. So if we decide we want to do more certain, and we got to go through a year or two of putting there, and through like all this to say, oh, that was something, we can afford something closer about this, up and down. It's just where they live. They live over it. They live in their place. In money. More up of it. So that's great. All day long. He said all summer long. And he's like, and all week for two, we get these figured out. I guess he has. Yeah, we have that. And he was like, yeah, that's not good. He was the separate for work. Right. Well, I always told my kids that one of the things that it's potentially, especially, I don't want to so but I can I mean basically this work New Jersey and I report it's basically work for training. And now we can try and it's just you guys would really get along together. Like personality in terms of just like love. Make sure that we get he lives out in UMass. Like the idea of checklist. Yeah, right. I'll ask him to do something. It is definitely mistakes. I don't. Anyways, I'll be back. Just, getting back now. I had I was the last, or in the last in person. I was there every Monday. And then I hadn't been back in 6 months. And then a couple of weeks ago, I had an intern that I hired from the University of South Carolina. He's working with, actually with the he was up. I met him and we were visiting him in South Carolina with Morphas stuff. And then he called me. So I got stop chatting. I don't think he was. Oh, yeah, I'll put the 10 on that. Thank you.
Should we go front? Yeah, right here. Is this the only slot that has 4 talks going on at the same time? No, there's no others, really. Yeah, I think so. Oh, maybe in the end. You're just gonna have to make do, I suppose. Yeah.
Hang on to the C3. Is there people in the office?
There is, yeah.
Really? I guess like. Oh, you know what? I knew about that. I just didn't know where it is.
What's your work profile? Are you like remote or are you like office flex?
That's it. Office flex.
Yeah. Well, if you want a desk, you can go up. I know that because I'm on. You're. They have to let the desk go. I would love if they started forcing. If they gave me, you know, I used to do it more, I'd be like,
Should it start? Okay. I'll try this one. Does this work?
Yeah. Yeah.
Okay.
Yep.
All right. Thank you. All right. So, hi everyone. My name is Alexander Bolyakov, and today I'm excited to talk to everyone about applying the lessons that we learned from fuzzing hypervisors to improve kernel security. And this work is, I'm an intern at Red Hat. This work is being done with my mentors here, Bandan Das and Stefan Hashnoje, and my advisor here at BU is Professor Manuel Aguilera. So we all know that testing is important, and usually when we say testing, we mean we have some sort of piece of code and we manually write test cases for this code, and we confirm that the answer is what we expect. And if the answer is not what we expect, we can catch that and fix the bug before it makes it into a big release or something. But if we look at fuzz testing, which is what this talk is going to be all about, it works a little bit differently, where instead of manually writing the test cases, we create a harness for our code, and then that harness randomly provides inputs to the code we're trying to test. And then we also write some sanitizers or some sanity checks to make sure that the code doesn't do something horribly wrong, like crash on a division by 0 error. And fuzz testing is a really powerful technique because obviously everybody knows writing tests is important, but writing good tests is quite hard, especially for complex pieces of software. Whereas with fuzz testing, you let the computer figure out which tests to run, and when it works very well, it catches some pretty complex bugs. And one important thing that really makes fuzzing effective is coverage guidance. So normally, if you'd just randomly provide inputs to your program, there would be a very small chance that the input really makes sense. Like in the calculator example, you can think if you provide random strings to your calculator, only a tiny fraction of those strings will actually be valid arithmetic operations or something like that. Whereas with coverage guidance, that allows you to break apart the program into smaller chunks and track each time an input reaches that part of the program. So if you look at this example here, in order to crash this program, you need to generate a input that contains the string of fuzz in 4 characters.
So if you think about randomly creating this, you basically need to, there's a very small chance that you'd randomly be able to create an input like that. But if you track the coverage of your program as you're executing inputs, and you only save the inputs that hit new coverage, then you break apart this problem into a lot of easier chunks. So first you find an input that has a length that's equal to 4, and you've covered that. So now you know that you have an input like that. And then eventually you'll find an input where the first character is an F. So you save that and you use that to mutate future inputs. And then you do the same thing for the U, Z, and finally, when you hit the last part, your program crashes, and that's how you know you found an interesting input and you've fully covered this piece of code. So that's a really high-level overview of fuzzing and coverage guidance. And so let me talk about Morphas now, which is our coverage-guided fuzzer for virtual devices and hypervisors. And what's the motivation for this work? Why are hypervisors and virtual devices in particular something that we want to fuzz? So we're all familiar with VMs and virtualization, whether we've used them to run a different operating system, analyze a malware sample, or anytime we use the cloud, we're usually running on top of some sort of VM. So one of the main promises of virtualization is the fact that if one of your VMs is compromised, the rest of the system is still safe. But if an attacker is able to exploit a VM escape attack, they may be able to compromise the underlying hypervisor and the rest of the VMs, which is really bad if you think about like a shared cloud system where there's multiple tenants running on the same hardware. So how do we prevent this horrible scenario from happening? Well, we have to find the bugs that lead to these VM escapes and patch them before they make it into releases. And one of the best ways to do that is fuzzing. So the problem with fuzzing, though, is if you think back to the calculator example a couple slides ago, that's a small function. These hypervisors are hundreds of thousands, millions of lines of code. And a large part of the code is actually these virtual devices, which provide this critical interface between the hypervisor and the VMs. And under the hood, these virtual devices are just implemented in a bunch of code, usually C or C++, which has exactly the types of nasty bugs that we want to try to protect against. So how do we fuzz this? We can't just call a virtual device function, because there's what we'll see in a few slides is that the way that VMs interact with devices is actually quite complex. So let's go over that. How do computers interact with devices, and how do VMs interact with virtual devices? Say we have our computer wants to draw a character on the screen. Well, there's no instruction that says draw a character on the screen. Instead, the CPU has a lot of instructions that read and write from memory. And it just so happens that some of these memory regions in our memory are actually mapped to devices rather than being mapped to normal RAM, which we're used to using. So if the CPU wants to draw a character on the screen, what it can do is find the graphics adapter's region in memory, its memory mapped I/O region, and basically do a normal write to that. And instead of going to RAM, that write will actually get routed to the graphics adapter device, which will show a letter on the screen. So that's a really simple way to draw a letter. But if we're doing something high bandwidth, like trying to write blocks to a disk or trying to send large packets over the network, that's way too slow, because each time the CPU writes to one of these MMIO regions, it basically has to wait for the device to handle the request, and it's a synchronous and very slow way of doing these things. So if we say we want to write a packet out on the network, instead what the CPU can do is put the packet somewhere in memory. And in fact, it can even do something fancier, like it can create a ring structure in memory and have it so that one of the indices on the ring is a pointer to the actual packet data. And then when the CPU is ready for the network device to send the packet out, it just has to write a pointer to that ring, and then it can continue working on something else, while the network adapter will asynchronously go and access that data in RAM and pull out that packet data and send it out over the network. And from a fuzzing perspective, this is quite complicated. This creates quite a problem because it means that the input space for our fuzzing inputs can basically be all of memory, um, and that's quite a big problem because if we think about our input to the calculator example, it's a few characters, right? Maybe a few kilobytes. That's what normally fuzzers are good at working with, inputs that are a few kilobytes in size. But for something like RAM, even if we take like an ancient 32-bit machine from 2003, this is going to be like a 4 gigabyte input space. Way too large for any of these fuzzers, even with their coverage guidance. So if we look at a real crashing input for one of these virtual devices, this is a real input that crashed the E1000 virtual device in the QEMU KVM hypervisor. These inputs are not just, they don't just interact with various addresses, they're also highly semantic. So even though this doesn't seem like a very large input right off the bat, if we actually look at this, it's the addresses and the values here are highly semantic. And what I mean by that is that the addresses of these MMIO and port IO regions depend on values that were previously written in the input. So first, what happens in this input is this first part is actually doing PCI configuration. It's not even talking directly to the E1000 device. And that PCI configuration creates this MMIO region, this green MMIO region, which is based on that green address up there. And then once we're actually communicating over MMIO, then our DMA communication kicks in, where we specify the address of a DMA buffer. And then we tell the device to actually access that DMA buffer. And the bug here was actually that the DMA buffer contained a circular reference back to the device's MMIO region. And this created sort of an infinite loop type issue. So you can see that these inputs are highly semantic. It's very unlikely that you'd just be able to randomly generate this by just passing like strings like in the calculator example. So inputs can interact with virtually any address. And how do we deal with that? Well, there have been prior approaches, and bug bounties for these virtual devices for hypervisors have been in the hundreds of thousands of dollars for some of them. So obviously, this is a problem that people care about, and people have tried to deal with it in the past. So there's approaches that ignore parts of the input space, such as all of MMIO or all of the DMA space, and they have been actually fairly successful when they first started out, because it turned out that even the simple devices that don't have DMA still have bugs in them. Then there are approaches that depend on a scratch buffer, and what that approach uses is it tries to place all of the DMA activity in a small region in memory, and then use heuristics to sort of steer the devices to use those particular that small scratch buffer as the region that all of the DMA activity targets. But because this is a heuristic, and as we saw, the DMA buffers can be something complicated like a ring buffer, this only can exercise like the simplest types of devices. And then we have the grammar approach. So what we'll see both here and in the later when I talk about the kernel is that when fuzzer developers hit these tough targets and these hard problems, oftentimes what they resort to is writing grammars. So, and what this means is you sort of help your fuzzer out to target individual devices by writing a grammar. So before you can fuzz the E1000 device, you write a grammar for that E1000 device, which tells the fuzzer exactly where the DMA buffers need to be placed, how they need to be connected. You're basically writing a lightweight driver for this network device before you can fuzz it. And that is effective, but first of all, it's very difficult to write these grammars in a accurate way. You need expert knowledge about how this device works. And there's dozens of these types of devices in hypervisors. So really, it's a lot of effort for every single device, and it's really time consuming. So our approach, Morphas, tries to take a step back and look at the problem again. So we have this problem of the enormous input space, but at any single time, there's only a few memory mapped IO regions, and then there's some DMA activity that can be anywhere in memory, but it's also limited to a small range. So what Morphas tries to do is take this enormous input space and reshape it so that what the fuzzer sees is only the regions that are actively engaged in I/O, and then we can ignore the rest of the unused or unengaged address space. And that by doing that, we can make it so that the inputs interact with only a few pages in memory, for example, and that's tractable for an off-the-shelf fuzzer like AFL or libfuzzer. So this is great, but how do we do it, right? Well, remember, let's look at the case of MMIO first. MMIO is that example with the character on the screen. Remember that how that works is the CPU can interact with a bunch of different devices. Most of them are going to be, or can interact with a lot of, with different addresses. Most of them are just going to be reads and writes from memory, but some of them are actually going to be hitting these memory mapped I/O regions, which need to be handled in this special way, where instead of just changing a value in memory, we want to draw a character on the screen. And if we look at this from the perspective of a hypervisor, which is just code, that basically means that for all of the hypervisors we looked at, there's something like a table, which represents the currently active list of memory mapped I/O regions. So, and that the hypervisor needs this because it needs to know which addresses, which accesses it needs to trap on, and which it can just write directly to memory. So as the fuzzer, what we can do is we can simply hook into this table, and then we know we have a perfect view of exactly the current list of active memory mapped I/O regions. So that's the MMIO part of the equation. What about DMA? DMA was that mode of communication where we can basically write our data anywhere in memory, and then we just need to provide a pointer to it to our device. So this is more complicated because now the input can interact even with normal memory. So how do we address this case? Well, let's just ignore DMA and fuzz MMIO. Eventually, one of our MMIO operations will cause the device to initiate a DMA access. And that access is going to hit somewhere in memory. We don't know before where it's going to hit. And we don't have any interesting data there. So how do we actually provide fuzzed data at that location? Well, again, this is code. And for all of the hypervisors we looked at, they feature something like a DMA access API, which handles stuff like translating guest addresses to host addresses. So basically, when you want to fetch something from the guest's memory over DMA, you always have to use something like this API. And so as the fuzzer, again, we can hook into this API, pause the access by basically setting a breakpoint in the DMA memory access API, and then populate the corresponding region in memory with fuzzer provided data just in time. And then once the fuzzer data is there, we can resume the access, and just like that, our device is now reading fuzzer provided data. So we put all this together and implemented it for QEMU, the popular QEMU hypervisor. So first you need to add those hooks that I just talked about, and then you need to build out the rest of the fuzzer harness. And this basically means, the fuzzer, like in the calculator example, the fuzzer provides us with some bytes, and we need to convert that somehow into these I/O interactions. So in our case, we use the libfuzzer. So how do we convert just these bytes into I/O operations? We implemented an interpreter, and all that interpreter does is it interprets the bytes in the input into sequences of port I/O, memory mapped I/O, and DMA operations. In order to handle state, so if you just provide inputs to a hypervisor without doing any cleanup in between, eventually you're going to have like all the pixels are going to be set on your frame buffer, for example, or something like this. And what will end up happening is even if you do find a crash, you won't be able to reproduce it because there's a lot of that dirty state that was already inside the hypervisor when you ran that crashing input. So to avoid that, we want to reset the state in between each individual input. And to do that, we added a fork server, which just forks the process and runs everything in a separate context for every single input. And then finally, we have this unbending stage that we need to do after we find a crash in order to sort of remove the need to use our DMA and our memory mapped IO hooks. So we implemented this for 2 hypervisors, for QEMU and for Beehive. 30, we looked at 33 virtual devices in total. We fuzzed each device for 24 hours, and we found that Morphas achieves 81% coverage overall, which is higher or equal to previous works for 13 out of the 16 devices. And remember, some of the previous works actually relied on manually written descriptions for these devices. We wanted to look specifically at DMA because DMA is so complex, and we found that the way that we do DMA with the hooks is improves the coverage significantly for 24 out of 33 devices. And the reason this number isn't higher is because some devices don't even use DMA at all. We found a lot of bugs. So in total, we found 110 bugs, of which 66 were new or only found by our fuzzer. Out of those, 29 were assertion failures, 8 stack overflows, 8 null pointer dereferences, 7 use after freeze, 7 buffer overflows, and 7 miscellaneous bugs like floating point exceptions. My favorite part about this project is that it's upstream. So we were able to upstream Morphas into QEMU, and it's continuously running for and fuzzing virtual devices on the OSS Fuzz platform for continuous fuzzing. So for OSS Fuzz has reported over 200 issues, and we've put a big emphasis on making bugs and reproducers easy to use for the developer. So when we get a report from OSS Fuzz, it's simply that binary input that you pass into the fuzzer, and it needs to be run through the interpreter. But we don't want the developer to have to worry about any of that because maybe they're not familiar with the fuzzing infrastructure. So we convert that into a standalone QEMU reproducer that you can basically just copy and paste into your terminal, and just like that, you've reproduced a virtual device bug. And you don't need to worry about any of the details about how the fuzzer works. So in summary, Morphas lets us bend the input space to make it conducive for fuzzing. And that lets us use time-tested fuzzers like libfuzzer to solve this problem. And we're able to fuzz basically any device after the hooks are implemented in the hypervisor. And we don't need any descriptions or grammars for individual devices. So how does this apply to the kernel, Linux kernel? Linux kernel is a much larger target. The hypervisor QEMU is a couple million lines of code. The Linux kernel is 30-ish, last I checked, 30 million lines of code. There have been thousands of CVEs reported in the Linux kernel. It's a very active area for security research. Lots of people are doing security research over the Linux kernel, and the main interface that people tend to look at is the system call interface. This is what user space uses to communicate with the kernel. A compromise of the system call interface could lead to something like a sandbox escape, a privilege escalation. So this is how your unprivileged, compromised web server can escape its privileges and reach a root shell, for example. And then in the worst case, you could cause hardware damage, because if you're able to compromise the kernel, you have basically raw access to these devices, and you could potentially find a way to damage them. So obviously, people have looked at fuzzing system calls. What are system calls? Just a brief recap. It's how we basically do anything to communicate with the outside world as a user space program. So if we do just a simple printf in our C program, this converts into a write system call. And a write system call, very similar to printf, but instead of it only taking the message, it actually takes a file descriptor number, and then it takes a pointer to our hello world string, and then it takes the length of that hello world string as well. And you can actually write different versions of this hello world program. This one is directly using the write function, which is basically directly hooked up to the write system call. Or you could even replace that with a call to syscall where we replace the write with the number of the write system call. So there's a lot of different ways of achieving the same thing, but the main thing is this is how user space interacts with systems. And you know, there's a lot of these. There's hundreds of these system calls, and if you provide some sort of weird arguments and you fill some pointers with malicious data, you could potentially hit a bug. So this is something that was found by the syscaller system call fuzzer, which I believe triggers some sort of heap error in the kernel. So you're just writing, you know, the same C code that you'd use for like hello world, but you're providing malicious arguments to these system calls. I just mentioned syscaller. It's the most successful Linux kernel fuzzer. It's found and reported thousands of kernel bugs, and it's tightly integrated into the kernel workflow. So what's not to love? Why can't we just use that? Syscaller relies on descriptions, which I briefly mentioned when I was talking about Morphas. These descriptions are very difficult to run. So to write for every single kernel interface, you have to write these expert descriptions. For example, there's these boxes up here. This is actually 2013 lines of description code that syscaller uses to fuzz KVM. KVM is the Linux API for providing access to hardware virtualization features. So you know, KVM definitely isn't the most simple API to use. There's a lot of different options, so that's why it requires all of these descriptions. But you know, if you think about the fact that an expert had to manually sit down and write this, and you realize that there's 30 million lines of code, and KVM is just a tiny fraction of all that code, the problem is apparent. You know, this doesn't scale to the size of the Linux kernel. So what we're doing is we're looking at this from the point of view of what we did for Morphas. So if you look at what we did for virtual device fuzzing, what if we want to do kernel fuzzing now? Well, in virtual device fuzzing, we had ports and we had memory. For kernel fuzzing, we have what kind of arguments do we provide to system calls? We provide file descriptor arguments, and we also provide pointers. So we also provide memory arguments, just like we did for virtual devices. And you can see sort of how this ties back into virtual device fuzzing. Both kernels and system calls take pointer arguments, which make fuzzing them quite complicated. Also, kernels are really stateful and they're large, so you can't just use a fork server to fuzz them, or at least the way that if you want to reshape the kernel and you want to use and you want to effectively fuzz it with creating reproducible crashes, you can't just use a fork server. So in the ancient days, the way people did fuzzing is they just passed inputs over and over again to the program, but that causes state leakage. You could manually clean up the state after each input, but this is tough to do, especially for large targets. You could use a fork server, but this breaks down for large targets, again, like browsers and kernels. So what we are doing instead is we're creating a snapshot fuzzer, which runs the entire target, in this case the kernel, inside a virtual machine, and then it snapshots and restores it in between inputs. And this is actually the subject of an ongoing Google Summer of Code project for the CUMI organization. I'm really excited to see what the student will be able to come up with for that. So yeah, check that out if you're interested. So back to the kernel and the input space. Basically, the way our fuzzer works is we do the same type of reshaping where we normally, if you'd provide random arguments to system calls, all your system calls would be invalid because the pointers would be pointing to pages that don't exist, and your file descriptors would point to files that don't exist. So instead, we add hooks to both the memory access APIs in the kernel and the file descriptor APIs in the kernel. And that allows us to reshape the system call input space and make it so that our randomly provided arguments are actually valid, and they point to valid fuzzer provided data. And so here I have this box with around 8 lines of code. This is the description that we use to fuzz KVM, that complex API that I showed a few pages back with 2013 lines of descriptions. Our fuzzer does it with 8 lines, and we achieve higher coverage than syscaller. So our fuzzer is able to randomly create fuzzer-provided VMs, fill them with instructions, do all this interesting stuff in order to exercise the KVM code. So unfortunately, I don't have too much time to go into the kernel fuzzing work today, but if this was interesting to you, definitely check out our related writings. So there was a Red Hat Research Quarterly article about the hypervisor fuzzing. Then last week I presented at Usenix Security the hypervisor, the final version of our hypervisor fuzzing project. And then just today, Red Hat Research Quarterly for 4.2, there's an article that goes into more depth about the hypervisor fuzzing as well. So definitely check that out if this sounded interesting. And with that, I'm happy to answer questions. Yeah. Yeah, I can. Yes.
So you mentioned that you have to give the fuzzer access to a table that sort of maps where in the memory space, you know, the hypervisor can access physical parts of the machine.
Yep.
Are there any like security risks or considerations you had when you made that decision? How did that?
Yeah, so the fuzzing process sort of runs entirely offline, so it's not running like security sensitive workloads. This is something we run separately, and then we use it to find bugs, and then we fix the bugs. The actual version of QEMU that people run on the cloud, it doesn't have these hooks active or enabled. Yep. Anybody else? Yeah, yeah. Yeah, so the QEMU hypervisor or fuzzer is tightly integrated into QEMU, so it's definitely been a process to figure out how to report these bugs. But yeah, bugs are all in the either reported to the security mailing list or on the GitLab issue tracker for QEMU. There's I think around like 16 or 17 have been assigned CVEs or so. So. Yeah. All right. Thank you for listening.
All right, thanks for coming to my talk. After a great talk about how to protect the kernel using fuzzing, I'm going to show you how to break the kernel in 100 nanoseconds. My name's Tommy. I'm a PhD student here at BU, and I'm a Red Hat intern. I work with my advisor, Jonathan Apavu, and many mentors, including Professor Ron Krieger, many Red Hat mentors like Daniel, Larry, Uli, Richard, others. Yeah, so I work with some PhD students and Red Hat interns. Special shout out for this talk to Arlo, who's helped build much of the system that I'll be talking about, including an ARM port, and he's created almost all the visuals in this talk, certainly all the good ones. Let's see, also Ryan, a Red Hat intern who's applying to work here full time, who's been building features like a madman and collecting performance results. So wish he could be here. Myself, I'm graduating soon, hoping to find a job if I don't embarrass myself here. So let's get started with the recently edited title. Okay, if I had to put this talk into 2 sentences, the idea is that we're going to consider what becomes possible when application threads running in user mode can temporarily, or for as long as they like, take advantage of the full privilege and access of the supervisor mode of execution. And while this idea might sound radical, we argue this approach offers a natural way to optimize applications, and that it has a close analogy to existing systems in the Linux kernel, namely the kernel module subsystem that we know and love. All right, so the scope of this talk is pretty wide. We're talking about phones, laptops, data center servers running on hardware that implement multiple protection domains. This talk will make contact with the world of general purpose operating systems like Linux, as well as some specialized OSs. And I'll start with this diagram, thanks Arlo, to start to build a visual vocabulary. Right, the Linux world, it multiplexes a bunch of processes, containers, virtual machines running on that shared monolith. And notice the upper half of this diagram, right, where application code runs in user mode, and the lower half where the kernel runs in the supervisor mode of execution. So I'll jump right in. What I'm proposing, I call it a chronokernel. The basis of the proposal is simple. It introduces a mechanism, so a mechanism going into a general purpose operating system that allows application threads to temporarily enter that supervisor mode of execution, right? And once there, it can read, write, execute any byte, in the kernel, anything that that's on that system, and it can execute privileged instructions. So if you just came to these academic talks for some jargon, I'll try to deliver here. All right, so the mechanism, it performs a decoupling, right? It's orthogonalizing 2 dimensions, the code base, so user kernel code, from these hardware modes, supervisor and user modes of execution. Right, and what use is academia if you can't give your ideas fun names like that? It's a bit of a reach. So the idea here is really at one time a thread might run with privilege. You can see that demarked, I don't know if you can see that in the back with a deputy badge. So at one time you might be running in privilege, and tens of nanoseconds later, you're back to just user mode. And then maybe 100 nanoseconds after that, you're running at privilege again. So user execution can take on this kernel privilege on a per thread granularity, right? Potentially 1 or more of threads within a process, or maybe any subset of threads in the system. That's the idea. Why? All right, well, the whole purpose of this is to meet our application's requirements, right? And we'll get more into that, but when you're running at privilege, you can do a lot of stuff that otherwise you can't. You can exploit the kernel's internal API, right? Cracking that thing open like a nut and reaching in like a toolbox and grabbing whatever piece you happen to need. We can use this like in the UKL talk to shortcut system paths. It allows applications, allows processes some degree of introspection in their ability to look at their own representation, like look at their own page tables. And it allows them to directly interface with hardware and devices. So to get in there, let's start with a zoom out. And let's take a brief detour into the world of sports. The Red Hat intern that I've been working with is a big soccer player. So I thought we could get some motivation here, right? Each position on the field, defender, midfield, forward, keeper, they all require a very different set of skills. You can see them on this radar plot. I don't know if you can read it in the back. Dribbling, curve, long passing, right? And the idea is that, each of these positions requires a different set of them. And if you showed me a player's skills, I could probably tell you which one they fall into. You need to be able to bend it like Beckham playing in the midfield, and unlike Buffon, who's a keeper. Similarly, classes of applications have different requirements from the operating systems that run them, right? And so here's some contrived examples. A container orchestrator who cares about security and correctness, extensibility, a machine learning application that's just trying to get through the workload, and a high frequency trading app that's trying to beat the market with low latency. For one operating system to well serve the union of all of these applications, it would have to be able to serve the maximum along each of those dimensions, right? And of course, we recognize that these different axes are in tension, right? If you want more isolation, you're going to pay perhaps in the degree of sharing that you're able to support. And so the attempt to simultaneously satisfy these goals under the constraint of those tensions is why building operating systems is hard. We can think of it almost scaling with the area of this made-up polygon. So in practice, general purpose operating systems don't succeed here. They make compromises. The isolation of your container orchestrator implicitly trades off against the latency of your high-frequency trading app, right? And when, so if your application's requirements are safely within inside that orange bound, what the general purposes operating systems trade-off space, then you're happy. There's nothing else to do. But if it lies outside of that hull, that's when we might have to take action. So when you can't solve a problem in general, it's often easier to decompose it and to specialize, solve the special case, right? Footballers don't try to play every position. Some approaches to this include kernel bypass, where you kind of unhook some resources from the general purpose OS, specializing to your application. That come with its own set of drawbacks, right? We're not making use of that kernel code. We're unplugged from accounting services like C groups. We might be polling CPUs. Another option is to build specialized OSs, right? Just choose a subset of those and serve them really well. This comes with massive redundancy, programming effort, really fractures the community. So for the purpose of this talk, I'll talk about extensions as coming to the rescue. And I'll offer a definition. Extensions are structured tools that operating system designers provide. Applications will use extensions to renegotiate their system interactions. So this could look like exposing new kernel interfaces, right? Modifying existing kernel paths. If you're willing to put in some effort here, some effort to identify what is particular about your application, then you can get kind of this best of both worlds, the full general purpose operating system underneath you while exploiting application specific knowledge to your advantage, right? With the big hope that we can start to throw this into libraries and actually get some amortization on these in the long run. So, okay, the OS literature is full of examples of operating systems that take great pains to allow applications to benefit from these extensions without compromising on the other axes, right? So you could think about the way that this diagram preserves the other dimensions while pushing out on the latency axis. So they use a lot of different techniques to pull this off. This is really just for the geeks, but what I'm trying to show you is all these different extension techniques and their mechanisms, right? So the exit kernel, you're linking with system libraries and you're running in protected address spaces, right? You're downloading code and running it with a safe language or software fault isolation. You're swapping user servers in a microkernel. You're using type-safe languages to implement your extensions. You're using transactions, software transactions that can undo the changes you make if you break an invariant, right? Or maybe you're even using direct access to virtual hardware, but you're running it inside a VM, so it's safe if it goes off the rails. So what I'm emphasizing here is the safety of it. We're preserving all of the prior points, and we're making some progress on a given access. So let's talk about something completely different, kernel modules. So, coming from all that hard academic work, how do we get this free lunch? How do we avoid compromise? Imagine my surprise when I bump into the Linux module system, right? And here the kernel, right? It can arbitrarily extend at runtime through dynamic linking. We can extend that protected code base as if you had edited the kernel code yourself. There's nothing safe about this mechanism other than it hiding behind sudo access. So you certainly can go and implement an extension that conforms to the other axes while making progress on one. But really the power comes in down here where you can, for example, compromise on one axis for an even bigger win on another, right? So the way that I see this is there's a wide spectrum of use cases here. We can do it perfectly safe as we do with device drivers, right? This conforms to all of your normal expectations about kernel code. Or what I do is put print statements on performance critical paths to pull out kernel pointers and exploit them for my own reasons, right? Just breaking every property of performance and safety. And not only these extremes, there's meaningful intermediates, right? Systems like BPF that put some safeguards around what you do, right? It makes it a bit harder to shoot yourself in the foot, but this is not a system that's going to withstand malice. We still put this behind the sudo interface. So Spin, one of the systems that I talked about a while ago from the 90s, right? They have this pejorative term, right? In general, we prefer to avoid using object files that are safe by assertion, right? We want to use compiler verification, blah, blah, keep everything safe. But it's worth noticing that our Linux kernel is only safe by assertion, right? The modules that we use to implement our device drivers are only safe by assertion. The only checks on this thing, the only breaks are human review, tools like the fuzzer we just heard about. There's no guarantees about these things. But I'd argue that this isn't a bug, right? This is actually the key to unlocking huge productivity. The module developer is empowered to create whatever they need, right? Whatever software fits their use case. Kernel modules enable so many of these tools that I want, right? Each of them is cooler than the next. K-patch, you're hot patching in different functions into the kernel. K-probes, you're putting handlers wherever you want. System tap, people are building tools around techniques for debugging this thing. BPF, as we mentioned. But there's also a set of drawbacks, as with any tool, right? So one is the language constraint. We have to conform to the kernel model and write C code. I really can't overstate this one. No application libraries, right? We're in this sanitized kernel environment, and we only have the tools that are placed there often for their own safety, our own beliefs about their correctness. You have to conform to the kernel programming model. You have finite stacks. You have to build it to live in some sequestered part of the address space. There's no POSIX interface underneath you. It's probably a lie about the system call API, sorry. And it has this contrived lifetime, right? The insertion and removal of a module, right? If you're doing application specialization and the tool you're exploiting has a different lifetime, it just feels unnatural. I would like modification to the kernel to go in with the application and come out as it dies, not needing to orchestrate it separately through a bunch of scripting. We also lose our association potentially with users and their credentials. All right, so there's perfectly good use cases for kernel modules. Packaging device drivers is a brilliant one, right? There's 10 gajillion device drivers that would bloat your kernel to an insane size, increase the attack surface. So the ability to insert them and remove them whenever you want, that's awesome. That shouldn't go anywhere. But when it comes to application specialization, for example, using BPF to put a cache in for example, for memcached, there seems like there's a disconnect here. Are we really just taking application code, wadding it up into a ball that will conform to the kernel's execution mode, and throwing it over the fence to where we just happen to already be running privileged instructions, and we just happen to already have file systems and memory allocators over there? Something feels a little bit wrong here. So my question for the purpose of this talk is, are we living in a world of coupled thinking, right? Where code base and privilege are conflated to a particular location, right? We do this kind of code here in this location and in this mode, and the opposite. So I hope I can throw a jab at UKL after having worked on that project for years. Right, some folks are peddling an approach where you take your whole application and your user libraries, you jam them up into a giant wad, and you cram them down into the kernel. And this is one of the coolest projects out there. The amount of cool properties that we got out of build time specialization, the amount of cool unikernel techniques that this let us pull in, right? This thing's awesome. It's worth a read if you haven't checked it out. But for the purpose of this talk, I'll just be a little mean, but I want you to ask, right? Do you really want all of the threads of your application down there in the kernel all the time, right? Because a lot of them aren't performance critical, right? What if you could just pull out the one piece of it that actually has those requirements, right? And in our decoupled model, that's exactly what you'd be able to do, right? So instead of moving application code down, move the access up, right? You want access to this privileged mode where you can execute these instructions. Instead of throwing your code over the wall, just bring the wall up to you. So I'll give an example, or I'll give a definition of this thing, the chrono kernel. Come on. So here we go. Any system that makes use of multiple hardware privileged execution modes. Okay, so we have multiple modes of execution, and you're offering first-class support for user threads to enter and exit it. We could talk maybe in another context about what we could do when we provide this to the kernel, but for the purpose of this talk, we're using multiple hardware privileged execution modes and first-class support to enter and exit them from the user context. So what's similar to the module world, right? They're both only safe by assertion, as with the kernel itself. They both can safely punch out, preserving the original expectations about how that system works. Or they can make these aggressive compromises to maybe get bigger wins, to unconstrain themselves from those other design points. This slide's overwhelming. Okay. So what's different, right? This one's key. Incremental improvement, right? Just slice out that one path that you care about, that you need better performance on, that you need better real-time guarantees on, that you need better security properties from, right? Just slide out, just grab that one piece and then bring all your tools and leverage them against it, right? If you're well served by the general purpose operating system, run it at low privilege, right? Where your null pointer dereferences are seg faults, not panics, right? So when you are running at privilege, we can function call from the application, right? From the application into the internal paths of the kernel. We can open that up. We can look at our, as I said before, we can look at our own representation. We can directly access that hardware. Here's a key one, right? Access to application libraries, just the whole huge world of software. We haven't put ourselves down into that sanitized kernel environment. We're building to the application programming model, right? Whatever linkage you want, you're on real stacks, unlike these modules. We're not building this to hide in one particular spot of the virtual address space. Do this in any language, as I'll get to. Anything that can make a system call can take on this elevated privilege. It can become, it can enter this mode. Here's one thing: you have the option to be associated with the lifetime of the application, right? So the choices that you make to prepare that environment, right? You can do that as your app begins, and you can clean them up as it ends, right? These aren't separate insert, remove tasks, although we do make use of that lifetime as well. All right, there's a couple more points. So the point is that these are both interesting tools. Use them for whatever fits your use case better. So let's get into the implementation of this thing. So we have a prototype running on x86-64, and we have a proof of concept running on ARM64. So we're kind of arguing that we're hitting a wide swath of compute that people care about. So we've shown that it's possible here to retrofit a general purpose operating system, Linux, to turn it into a chrono kernel. This was done by introducing a mechanism that we exposed through the system call interface that allows application threads to toggle in and out of privilege. And this required an exhausting 357 lines of code changes. So let's dig into that a little bit, right? So 300 lines of code that are changed, right? Well, the idea here is that we're exposing a primitive, right? The primitive is the ability to enter the protected mode, the privileged mode. And once you have access to that primitive, you can write your own executables that make use of it. So a lot of this code that normally you insert into the kernel or you write into the kernel source code, we can just have those sitting as executables in our file system. So here's a simple example. I won't get into this too much, but on x86 hardware, when you're trying to execute application code in this privileged domain, one of the first things that's going to happen to you is you'll page fault on your stack, right? This is something that kernels don't do. They pin their stacks. You don't go off the end of them. And that's going to immediately go into a double fault. You're trying to run a handler on the very page that you are trying to fill. So you can solve this in a number of ways. One of the ways is to force the processor to unconditionally, so from whatever mode you're in, always do a stack switch onto a known pristine kernel stack. It's called the IST mechanism. And you enable it. It's pretty easy. You flip one bit in the interrupt descriptor table. All right. So here's a dumb picture of. So imagine you're on a given core. You're on core 3, and you have an IDTR, the interrupt descriptor table register, which just holds a pointer to your interrupt descriptor table. Here's my executable. It lives in the file system. It's called the IDT tool, right? I wrote it in C. I could have written it in Rust. So I say IDT tool on core, I guess we're on core 1, sorry. I say enable the IST, right? So what does this do? It copies the IDT. We make a copy of it. We flip that one bit. So now page faults will be served on the IST stack unconditionally. And now we're no longer susceptible on that core to these double faults when you run out of stack. And now you can ask all the fun questions, right? Where do we allocate that new IDT? I don't know. I've given you the power, right? Do you put it in application memory and you pin it? I've done that. It's not fun when it gets swapped out. The whole system reboots. But that is an option. You want it associated with the lifetime of your application, go for it. Or maybe you just want it to live in the kernel forever until you reboot. So reach in as you can do, exploit that internal kernel interface, call whatever kmalloc and get your page, and there you go. Point your IDTR at it. I think you're supposed to have these slides where you talk about performance. So let's talk about an example. Redis, it's a well-known application. It's a key value store, or often used as a cache. So the idea here is just like UKL. I think you heard an example of this earlier today. We can exploit these kernel internal functions that we've opened up to shortcut critical paths, right? The general purpose operating system is using its virtual file system layer to support everything under the sun. But I know that this is Redis. I'm just doing TCP sends, right? So we have some ways to exploit that shortcutting, right? One example is you call into, so skipping all the system call entry code, VFS layer, we call right into cases read and cases write. Yeah, so when you call in at that point, you do cut out some of that entry exit code. You get a modest improvement on your mean latency, your 99 tail. But the really fun shortcuts come in when you get below that VFS layer, maybe all the way just before the protocol layer, where when you're calling in, what used to be reads and writes are now specified to the down to the protocol what you're doing, calling into TCP send message, receive message. And the numbers that we're coming up with now are on the order of the results that we're reporting from the unikernel numbers. So this definitely needs more, more work. We'll keep cleaning these up. But as Ryan sends me these numbers, it's impressive to know that without any major re-architecting of the software, we're still able to exploit some of these pretty impressive shortcuts through the software. I think this talk's basically over, but I think just one fun place to leave it is here. So I stole this from the Snap paper recently, Google microkernel approach. But if you think about the way that our applications usually call into to make these network operations, the applications will call into the kernel, who will take care of interfacing with hardware. Some approaches you could think of, maybe DBDK, take an application, they bypass the kernel and talk directly down to the NIC. In their model, and the model that I think is a fun headspace to play in for these tools, is imagine that we're creating, just like with the kernel modules, where we're creating those safe by assertion environments, right? So imagine that we've handed over our source code to the community. They read it and they say, "Hey, I like the way that you wrote that process. It looks very safe." What if unmodified applications can use it as their interface into accelerating their network traffic, for example, right? So here we have perhaps ABI compatible applications making shared memory writes into our deputized server, right? And we're letting that thing shortcut on our behalf, right? So I think that's a fun space where we're not just hacking up an application requiring it to be modified, but maybe we're intersecting it with a dynamic linker and interposing on its reads and writes, shuttling them off maybe directly to hardware. So I think that's a fun model that you could think about. So that's the end of my talk. Thanks for coming. Any questions? Farul?
Everything is already privileged, but like in this, you have to figure out which thread is important. So have you thought about that?
Yeah, so to the first question, where does this have applicability? I think this is maybe one of these primitives that you just hand people and they show you what can be done with it. We have some examples from data center networking, but I think there's a lot of places that we want to renegotiate our relationship with the kernel. So I guess I'll maybe punt on that, but if this kernel is getting in your way, I think finding ways to use our application specialization to make our lives better, and then to take those approaches and to put them into libraries so they can be reused. I think anything following that model. So I guess that's a full punt. But yeah, the other question I think had to do with how do you choose which threads should be deputized, should be given privilege? Well, I think the way that I think about it is, if the parts of your application that are well served by the general purpose OS compromise, if they land in there, then I don't have a particular reason to pull them out, right? When I'm unhappy with latency, or someone says, if we could improve the throughput, we'd be in a better spot. I think when you're not well served by the general purpose operating system, pull it out. Yeah. But I mean, generally, just from practice, initialization, teardown, it often interacts with a lot of strange tools, but none of it's performance sensitive. You pull out the part that you really care about, just profile it. And maybe it offers an approach where you take the path of least privilege. So much of the kernel code runs at privilege, I think, just because of this conflation, just because where it lives and because we don't have tools to make this decoupling. So I think there's large parts of the kernel that don't need to execute privileged instructions that we could think about. Maybe two things. So now I'm just rambling, but one is okay, we've retrofitted this into a general purpose OS. Now you can go and incrementally take your approach, right? Maybe the more fun thing to think about for OS nerds is how would you, Jonathan put this question to me. If you had access to this primitive from the start, how would you design an operating system, right? Would instead of creating, I need my scheduler, I need my virtual memory subsystem, I need this and this, and then, okay, all the pieces are in place, try to run something? Would you maybe just try to bring up the simplest user space possible, right? No virtual memory even, right? Just the simplest user space, and then writing these executables that just live in your file system. Could you create the system call interface? Could you create a scheduler and install it? So I think that's maybe a more like a very fun direction, is how would we do this from the beginning if we always had access to it? But I don't even know if I'm answering your question anymore. All right.
I observe there's two weird aspects to this. On the one side is it makes you think about a different way of bringing your operating system. So when I think about Linux, it's got all this, this VFS layer. It's got indirections everywhere, fundamentally, so it can be extended and customized to satisfy a variety of different workloads, right? So it's gotten really complicated to understand. Could you design it a simpler way? But the bizarre thing that you've done is that you've also made it so that you can take the existing really complicated thing and start just extending it. Like, what do you feel you can't do given what Linux is today? Because with 300 months ago, figured out how to make it. What things could you not do? Well, incrementally for your application based on where you are.
Yeah, what a cool question. No, yeah, so one part, and I know this isn't what your question turns on, but just to build some base, of course, in privilege we can do anything, right? But that's not what's interesting, right? So once you're given privilege, you can create anything. I think the question is, what is it natural to create? Yeah, so one of the things that I love about the UCal project is the opportunities for link time optimization, and that's been demonstrated now, is that when you take your application and you put it down into the kernel, you're doing a proper link between those worlds, and you have a really cool opportunity to optimize across them. I don't know if that's so natural in my model, so I've definitely thought about pulling kernel code out, maybe from the kernel itself to link into the particular sensitive path in the application, or maybe not even from the Linux kernel, but from a donor kernel, right? Jim worked really hard on EBRT and got some fast networking paths, so maybe I could link time optimize those into our deputized threads, as we're calling them for this talk. I don't know. I don't even think I hit half your question, but do you want to come back with anything? Can I try to answer that just because I have a terrible memory? Okay, cool. I promise. Yeah. So this is why I did this work with the modules. I think they give us a nice example where if you can insert, right, if you can dynamically link your code into the kernel, you can kind of do anything, right? All bets are off, right? We have some in-between compromises like using language tools and BPF, but really we fall back on the human approach, right? Read that code, run your fuzzing tools, right? And that safe by assertion property is sufficient for building the kernel, and it's sufficient for building modules. So that's the connection that I'm trying to make with this tool is you have privilege, right? You can hose the system in no time, right? Just hold all the cores, right? But the point is that we can create these, we can put them out to the community, we can vet them using the same processes, and then administrators with sudo access can start, for example, some of these microkernel-like servers running on our system that we unprivileged users might go in and interact with, right? So that's at least my argument. I don't know if you find it compelling. Yeah. And you had another question though. Yeah, so context switching has long been one of the tensions that we consider. Yeah, it is the case, right? The UKL code gets linked into the kernel, right? They literally produce the same executable, right? UKL has this awesome property where you can also run user space code that does suffer those context switch overheads. I think one important piece of this story is that people will get this wrong. They will say that that user code lives in a different address space from the kernel, and that's not the case, right? If you're not using kernel page table isolation, and I've tricks for when you are, you're just living in opposite ends of the address space, right? So it's not like we need to do a page table switch, flush caches, right? So what is different is the bits in the page table that say whether you can access that page or not, right? So when you're in privilege, I'm not thinking of a very heavy context switch penalty that you're paying. I'm making indirect function calls. I don't link as UKL does, where they can do direct function calls, right? I look up, I do, cat the Linux system map grep for print k, and then I find the address of it, and then I'll load that into a register, make an indirect call. They're not as fast as direct calls, but they're fast. So I don't think I'm really paying an obvious context switch cost, at least in a simple view of this. There are probably many subtleties that I haven't even considered, but does that speak to your concern? Yeah. Jonathan in the back.
So would it be fair to say that you're not a fascist, you're an anarchist? So unlike you now, unlike the system today, you're just fascist. And you're sort of saying, well, we're smaller.
Someone get help for this man. So we have a very sick man in the back of the room. Whatever helps me graduate. Whatever ideology I will. I'm not sure about fascism, but for you, I'll be an anarchist. Yeah.
Deputized it right before you even start, and stay that way for the entire lifetime of the system, and then it's UKL.
Yes.
On the other hand, because you now have the option to go in and out, you other points along the trade-off.
Yeah, that's incredible, and it's also where some of this thinking started. The question was, can this and can UKL be complementary? Could we even use this approach? Can we even use this chronokernel approach to multiplexing UKL environments? Right. I think that's the end of my memory, but yeah.
As general as possible. Modifying the page tables or running large parts of your application in space. How does this compare to like the IOPL system call? It's been around for like decades, and I'm like a security person. I know that there have been efforts to strongly prevent people from using that over the years. Just like theoretically, if you do an IOPL and you change your bits so you can access the like you be able to do all this stuff. And I don't think you need to modify the kernel at all, right? So yeah, just wondering how the approach compares to that.
Yeah, thanks for that. I think I'm pretty ignorant about that system call, and I don't know. Let's shoot me an email. Let's look into that. Maybe you'll save me a lot of time. Is there anything in particular that is that something you've used? Is that something you've disable interrupts? Nice. Yeah, can I mean, as an application, can I make a system call and then read CR3? Can I execute a privilege instruction? Cool. Then I guess I'll have to take a look at it and maybe start a new thesis. So no, but thank you. So I didn't talk about the libraries that we built around this, right? I hope my PhD doesn't hinge on these 357 lines of code. The real work is in building libraries that make use of it, right? What does it mean to interpose on interrupts, right? I talked about this IST mechanism. Same thing exists for page faults, right? There's this new check. You guys are always making Linux safer, right? Like in 5.8, it wasn't there. In 5.11, when you page fault, Ellie knows this well. When you page fault, there's now a check that says, okay, we're running the user page fault handler. What mode did we come from? Supervisor or user mode, right? Is this an exploit attempt? And now we use interrupt interposition to just tell a lie to the page fault handler saying, oh, we came from user mode, don't worry about it. So I think a lot of the work here has been in the tools that you build and you make use of once you've pulled that pin. And yeah, I'll take a look at it. That's awesome. If I can have 0 lines of code change to the kernel. Yeah, I appreciate that. Thanks. You had a question. I'll make you do it. Yeah, I think that would be fun. I haven't thought hard about that, but I think it's a cool tool. I think it has a nice complement to the kernel module. So I think that would be a cool process. Yeah.
May be able to elevate this API, these features into higher level languages?
Yeah, so as long as you can make the system call, you will return from that system call back in privilege. So I think in these high level languages, there's this fun idea of something that we've called positioning, right? So work positioning. You've booted the operating system, you started the user processes and daemons, you have started that interpreter, maybe you've compiled bytecode, right? You've taken all these steps to specialize your environment. Now you're in this high level language code, and now you make that system call, and even from the peak of that castle, you're still dropped into that privileged execution mode. So I haven't thought much about, okay, now you're there, what do you do in Rust or in JavaScript? But that's a fun space if you have any thoughts.
You hit the nail on the head. Like when you return, and then how you must have to have some higher level abstractions or some sort of patterns, and then that language would want to do something, some sort of module in that language that implements these like cool lower level operations.
Yeah. Cool. Yeah, sure.
So I keep struggling with this exactly. Besides the aerodynamics, obviously, what's the actual, relation? Where do these two things? I guess part of this is I think you have a tremendously flexibility on what's running and when it's running and which of the address spaces. I think that is the fascistic approach of the whole application is running there. I think it means so that the application doesn't have to change as much. Right? It's not like you're not building the new abstractions. You're just boom, this application is there, and now all these other things. So I think it might have more compatibility, and I think it's also like the mechanisms, the customizations are naturally then with the enhancements of Linux, we're going through an upstream process. And then once those are there, in some sense, then the anarchists can exploit them once they do the elevate call. So in some sense, I think part of this is how does it get built in? How does it get upstream? How does it capabilities? The right mechanisms are added to allow things to. You can override everything. You probably don't want to.
Yeah.
You probably want to use it.
Right.
Most of the Linux code, well, override just what you want to. PL kind of gives a path to having communities see those changes, see them in particular use cases. I don't think they're conflicting. I think it's just that you're broadening the use case of the extensibility.
I agree with you, and I'm glad that Ali's in the room because he can tell me if this is unfair. But I think that one of the real special parts of these unikernel approaches, unikernel Linux, is in the build time configuration, kind of the static compile time configuration choices. And from that point, once you've made them, you're stamping out these highly efficient executables, right? And I think that you don't want all these degrees of freedoms, all this dynamicity, right? Like you might want flexibility in a system that's going and actually executing these things. That's just one way that I've thought about it. But I don't know, Ali can punch back if he thinks that's unfair.
One of the things that I really like about this work is that, as Ron said, the packaging can be very easy in the sense that you can have a normal running system which just has the ability to elevate something, and then the rest is totally up to you. Or that's the only superpower you need. And after that, a normally running application which is dynamically loaded or is statically linked, whatever, you can elevate that and start doing special stuff.
Right, that's the primitive. Yeah. Thanks. Yeah.
Weird idea. What about the inverse? Like you start with the UKL, if you have a primitive that you can compute, would that be useful? Actually, that is something that does.
I made Ali write that kernel module, which all it does is a sysret to itself, and then seeing the barf as you couldn't execute the following instruction in user mode. So yeah, this idea of I called this a decoupling, right? If like there should be 4 choices on this wheel now, right? So if I can run user apps in privilege, can I run kernel code without privilege, right? So I think that's a really rich space. There's so much code in this kernel that doesn't need privilege to run. It's only there and running in privilege from my view, because of that conflation. So I think some reasons you might try to do this, we've talked about in our group, are debuggers, right? So running, there's these whole projects, there's these whole rump kernels, for example. It was a whole project just to run device drivers in user mode so that they're easier to debug, right? So you can imagine taking away privilege from this part of the kernel code that, and then putting constraints on it, right? No, you can only access memory from this region. No, you're not allowed to execute that instruction, right? So maybe this could lead to kind of debugging tools for kernel paths. Maybe this can lead to, right, in the microkernel approach, as we're pulling these subsystems out and running them at user privilege, we're crying about the context switching costs, right? So what if I can pull these out to user space and then pull privilege when I need those performance sensitive paths, right? So I think the fun thing to think about again is what Jonathan asked me was, what does it look like to start from scratch and build an operating system when this primitive has always been there? Yeah.
When consider all the potential configurations, was every time we came up with an idea, like we had this idea that we could actually build a sandbox model, right? That we'd actually be able to pull code out, we'd be able to actually put a wall around it and pick when and what it did that we were going to either transfer back into privilege or not. But even to engineer that, we realized actually we could do all of it if all we had was the elevate call. Like, we don't actually, many of these ideas, every time we come up with another use scenario, to even prototype it, we didn't actually need more than the base mechanism in order to enable that. That's why it felt right that we're actually separating out an idea that we can reapply in many different ways.
Yeah, when you have the power to take over those interrupt paths, you run the show. So, right, we're talking about building, executables that live in the file system that a user can type // and start executing them, right? User executables which go in, take over the IDT that allow you to do this type of kernel debugging and control it from a program that's written in whatever you want, C++. So it almost stands it on its head, right? You've become the entity that gets to start and stop these kernel paths. So I think that's a really fun space when you start to think about what you can do as that decoupling really takes. Yeah.
This whole security argument is that one of the things that we're seeing containers, groups of containers running together like Kafka containers or something into their own, on their own OS, right? Where all these trust issues kind of go away. So I think it's a really neat thing that's now happening is that virtualization has enabled single-use environments, right? And now we have mechanisms they can do with containers. We can deploy your logic like that. So it becomes feasible to have this deployment, not trust issues, because the kernel is being used by one application.
Mm-hmm. Mm-hmm.
Even if that kernel is part of a container.
Yeah,
I think it's really like a lot of these things. So doing extensible system, when we were doing those in the 1990s, the really old parts of Germany, that was all about we had one computer being used by a whole bunch of different users running a whole bunch of different applications, and that's how Linux was designed for us. We're trying to think, how can we extend it? And you're living in a world where you've isolated containers that be running their own VM, hardware isolation, and optimizing for that is a totally reasonable.
Yeah, this Moore's law transistor ubiquity, right? Like we can reach for, dedicate that hardware, whereas before it was how do we maximally share this between everybody?
It's not even dedicated hardware. Containers, with the Kafka container stuff, you're right. You're with its own VM and you're using a virtual mechanisms to do the isolation. So why are we doing it in the
you can't stop it.
Mhm. We see another hand. We're almost pushing an hour. This is awesome. Keep it coming.
I thought they all started.
Hey, great to see you. Yeah, doing okay. It's just like exam after oral defense, after talk, after yeah. So just trying to finish. I'm going to the Czech Republic to see the Red Hat Research Day.
Oh, you are?
Yeah. Have you been there?
Oh, yeah, man.
Yeah.
Yeah.
You gotta give me your.
When are you going?
September 15th is the research day.
So how did you?
Hugh was sending out emails and Heidi reminded me that of it, and so I'm just gonna go there.
So
and see what's up.
did you really book flights?
I'm about to. Yeah.
So there's two basic ways of doing it. You can either fly to Austria.
Yeah.
And take a bus as a bus service.
Yeah.
Or you can take a train. You have to stop. There's a stop from here to Bernardo. Or you can fly into Prague. And from Prague, you can take a bus from the airport to the train station, and there's a non-stop train. Right up. I would suggest you're a adventurous guy. I would suggest doing one on the way up.
Totally, I like that.
So, have you been to Vienna?
Never.
It's awesome.
Never been anywhere.
It's a spectacular place.
Yeah.
And if you get the chance, one of my kids did the study abroad in Budapest.
Oh, wow.
For his junior year of college.
Yeah. Didn't he get mixed up with the wrong woman? There was some passport issue.
He did.
Yeah.
Denies all.
Is this on?